brief overview of what is happening in the field of Majoranas. It's definitely incomplete, but I tried to relate, say, the physics of minimal models and topology to what is happening in real systems. This is mainly to orient you and give you some ability to interpret literature that you see appearing in new papers. Then I also introduced the tight binding simulations, and in particular, I explained the transport. The reason why I focused on specifically the scattering problem is because, on the one hand, it's the quantity that is often measured. People can easier measure conductance than they can, say, local density of states. Although, of course, if you happen to have a scanning tunneling microscope, then you can also measure local density of states with caveats. So today I'm going to demonstrate how the simulations of Majorana devices look like, and you could use a whole lot of software packages to do so. I'm going to demonstrate this using Quant. But the main principles are the same. And just to set the expectations, I'm in a weird situation because I need to balance between the physics of Majoranas and the software and Quant. You will also notice as a theme, nothing that I'm going to do is going to be numerically expensive or very complicated. The main difficulty, so over the course of today's lecture, I'm going to probably briefly cover the contents of, I don't know, 5-10 papers, and I'm going to really reproduce the results, which seems to suggest that there is not a lot of work to be done. However, the beauty of these devices is that the main difficulty is navigating yourself in the different parameter regimes and figuring out what is happening, what should be happening. So there will be quite a bit of that. I'm not going to demonstrate all the capacity of Quant. It's not a tutorial. It is, however, a demo of a part of it. So yesterday we discussed Majoranas. Just as a reminder, these are protected zero-energy states. They enable quantum computation. And today I'm going to focus on the simplest proposal for making Majoranas. It's also the most popular, and that's a nanowire. So a semiconductor coupled to a superconductor. A superconductor has a non-zero gap. There's a magnetic field causing Zeeman splitting. There's spin-orbit coupling. So altogether, these ingredients come together to a Hamiltonian. And by the way, as a quick reminder, I am still keeping an eye on chat and Q&A. So if you want me to discuss something in more detail, do write. So the Hamiltonian of Majoranas contains, contains the following terms. There's the kinetic term, that's the quadratic dispersion. And since we are interested in the semiconductors, we do not really care about the Brillouin zone physics. So this is really an approximate dispersion close to the bottom of the band. There's the chemical potential. There's the Rashba spin-orbit coupling. It's proportional to, it's linear in momentum with a proportionality coefficient being the spin-orbit strength. Now, the Rashba spin-orbit coupling couples momentum to the spin. So sigma here is the spin Pauli matrix. Now, since we are dealing with superconductors, there's also a particle hole or a Nambu spin. So the normal dispersion is duplicated with two signs, once with a plus for electrons, once with minus for holes. There's the superconducting pairing that couples electrons and holes, and finally, the Zeeman field that couples different spins. Now, a quick remark, and this is also a useful basis to write. So you will there are different bases in which one usually writes Bogoliubov-Duhem Hamiltonians, and frequently. So here I'm using a basis where holes are time-reversed electrons. So this is why. So the whole. So that means that that I use a basis where where the basis states are electron with spin up, electron with spin down, minus hole with spin up, plus hole with spin down. That ensures that the the part of the Hamiltonian that is even under time reversal enters with the Pauli matrix tau z, and no other entries, and the part of the Hamiltonian that is odd under time reversal enters with the Pauli matrix tau naught. So it has the same sign for electrons and holes. This basis happens to be more convenient, and also it is more straightforward to check, because in this basis, the S-wave pairing, essentially the only pairing that appears in condensed matter systems, except for some highly exotic situations, or the pairing that appears in vast majority of the superconductors, that one has no spin structure, and that is because a singlet pairing is proportional to the Pauli matrix sigma naught in this basis. This Hamiltonian has a topological phase transition when the magnetic field exceeds a square of the superconducting gap plus chemical potential, and that's when a finite nanowire should obtain Majoranas. So let's start with confirming this, and I am going to. So here I'm importing just some useful packages out of this. If you're familiar with Python, I'm of course going to use NumPy, the library for arrays. I'm using plotting. I am going to use quant, and the rest is for convenience. Now, in order to vary the parameters nicely, I'm also going to use a helper function interact, and just to demonstrate what it does. Here it is. I have a simple plot here, but now I can change its parameters. If I set y, and like this, I can vary the parameters and show what is happening. All right. So far so good. We are now set to compute the Majorana dispersion relation, and plot it and observe it and find the topological transition. So this is the Majorana Hamiltonian, basically the same equation as what I wrote above, just as this time written in code. There's the quadratic dispersion. I added all the Kronecker products of different Pauli matrices. And in order to convert it into a function that we can evaluate, I'm using this helper function provided by quant. This is here, the technical details are not really important. It basically takes care of the Pauli matrices and of all the different arguments. So let's take a look at the dispersion relations. This is still the continuum Hamiltonian, and try to identify the topological phase transition. So here are the parameters. Bx, once again, is the Zeeman field, chemical potential, spin-orbit coupling, and the superconducting pairing. Let's now set everything to 0. We see two parabolas, one corresponding to electrons, one to holes. If we turn on the spin-orbit coupling, the two parabolas split. The splitting, however, is proportional to the distance to the momentum itself. So this is all as expected. If we turn on the superconducting gap, we see a slight gap opening. Let's actually make it somewhat larger. Yeah. So we see that at 0 energy now, all the gaps are open. That is the effect of adding the superconductor. So now, finally, with these parameters in place, let's create a topological transition. And to do this, we are going to increase the magnetic field. So I don't know. Let's see. We expect a topological phase transition at 1 plus 1/4 and a square root. So at about 1 point something. So let's do 1.2. We see the two bands are almost touching. Actually, here they're not yet touching, but if we go to say 1.4, this gap reopens, and now we should be in a topological regime. If we go to smaller magnetic fields, we still see this gap did not close and reopen yet. Now, this is a continuum dispersion relation, but in order to simulate the Majorana spectrum, or we can also try to solve, for example, and compute the Majorana wave functions within the continuum limit. But a much more convenient approach is to discretize this continuum Hamiltonian, which means I need to introduce next nearest neighbor hoppings. And that would give this a similar low energy dispersion. This uses a finite difference approximation. And then I will have a finite system that I can diagonalize. So now this is where quant enters into play. So as a reminder, Majorana Hamiltonian is just the expression I introduced before. I'm going to introduce a template. So I'm going to ask quant to discretize this Majorana Hamiltonian. That gives me an infinite system because the Hamiltonian depended on momentum. And in tight binding language, the system contains one site that is repeated infinitely many times and one hopping. That's the nearest neighbor hopping. So let's look at the spectrum of this infinite, this time tight binding chain, to verify that the discretization worked as expected. So now we should see something that is nearly similar or nearly identical, but in tight binding. And indeed, so if we focus on the low energy dispersion, so state close to zero energy and zero momentum, we indeed see two spin split parabolas that come in two flavors, one pair for electrons, one for holes. This is all the same. The difference, however, now, of course, is that since we are now in tight binding, there's a finite Brillouin zone, and the dispersion relation is periodic. There is a limit. There is a question: how many neighbors does the tight binding model have right now? Can I choose how many neighbors I'm using when discretizing? So this is the nearest neighbor approximation. It uses the lowest order expansion of all the momenta. And indeed, it is possible to apply more and more precise approximations. But for the topological stuff, and actually also for the reasons of computational efficiency, usually you want to limit the range of the hopping to be small, to be the lowest. All right, so now let's confirm that the behavior is otherwise the same. So let's first of all, if we turn on the superconducting pairing, everything works. If we now we can use nice numbers that give a nice value when squared together. So 0.3 and 0.4 together, the square root of these is 0.5. We see we are exactly at the point of topological transition. If we take a higher magnetic field, we should be in a topological phase. If we take a lower magnetic field, we should be in a trivial phase. However, and this is already a point that people overlook more often than they should, one has to remember that we are now approximating a continuum dispersion. And if we start, for example, varying the chemical potential, it could look like this. now here the low energy, so here I tuned the band to half filling, and the low energy approximation does not work at all. There's a question to whether it's possible to try the simulation at the same time as I do it. So due to the time constraints, it's not so easy. What I would recommend, I will publish this notebook, and I do invite you to play around with it. But if you want to vary the parameters on your own, I do recommend to do it afterwards. And I did not yet prepare this notebook to be published. So for the sake of time, please follow, but you will be able to afterwards revisit the parts. And I do invite you to mess around with absolutely everything here. Also, this notebook is an extended version of a more dedicated workshop, which was focusing more on the quant part of the simulation. I will share a link to the recordings from that session. All right, so if we mess around with mu too much, we basically leave the limit of the continuum approximation, and we obtain a nonsensical dispersion, which is all too easy to forget. And that's because our approximation is valid when the energy is small and all the parameters are such that we are close to momentum equals to 0, with the physics coming from the finite bandwidth being a limitation of the precision. All right, so now we have discretized the Hamiltonian. We obtained a template that is an infinite wire. So now let's create a finite system and compute this computed spectrum and observe that we indeed have a topological transition. So to do this, we're going to use the same template. Remember, it's a single infinitely repeated site with a single nearest neighbor hopping. So I'm now going to create an object for the finite wire. This object is of a builder class. This is basically the object quant uses to define the different systems. You will see this class appear more and more. Wire template over here is actually also a builder by itself. It's this one is coming from the discretizer, but it is also a builder. So in order to simply create a finite wire, we take the template, we take the finite wire, and we add to it all the sides from the template that belong to a shape that starts at x equals to 0 and ends at x equals to 20. So let's do so. Well, actually, for completeness, let's also view that we have obtained a reasonable result. Let's plot the wire. And indeed, we see there are 20 sites. They all have no y coordinate to speak of, and x coordinate goes from 0 to 20. All is fine. Let's now look at the spectrum of a finite wire. And here we are going to, we don't have momentum to vary, but we are going to see how the spectrum changes as we increase magnetic field from 0 to 1. So let's take a look. This takes a moment to compute. So first of all, we see that so here the horizontal axis is bx. We see that at bx equals to 0, all the states are gapped, and moreover, we see that there are no states appearing between minus delta and plus delta. So this is exactly like we would expect. Now we also so for example, let's check that everything behaves correctly. Here we see that as we increase the magnetic field, the superconducting gap closes. Once we increase it further, the gap reopens. However, there are two states sticking to zero and that still keep on oscillating. There is a splitting, but it is much smaller than the superconducting gap. First of all, let's also see that we can understand why there are two superconducting gaps. And that, I will argue, is something we already saw before. So if we are close to a topological transition, you see that there is a small gap that closes and reopens and one that stays nearly constant. So this band over here is the one that comes from the finite momentum. This band that closes and reopens is the topological transition that happens at k equals to 0. Now, these oscillations, we do expect that Majoranas should appear at with zero energy. However, here they do not appear to have an energy equals to 0. Instead, they have a finite splitting. This phenomenon is dubbed Majorana oscillations. Although, of course, the actual Majorana oscillations are the neutrino oscillations that are searched in energy physics. This oscillatory behavior of the splitting is similar to Friedel oscillation, and it is due to the Majorana wave functions composed out of states that have a finite Fermi momentum. In order to check that it is indeed the case, let's reduce the chemical potential that reduces also the Fermi momentum. And if I am right, we should see the Majorana oscillations diminish and the coupling weaken. Yes, I forgot to show. Yeah, right. And if I do it, yes. So indeed, these oscillations diminish. However, an even easier way, and this is where the topological nature of Majoranas comes into play, if we take a slightly larger wire, so now with 30 sites, the amplitude of the oscillations becomes way smaller, and indeed it should be dropping exponentially with the wire size. So right now we have observed a topological phase transition, and we discovered Majorana oscillations. So just to give you a gauge of how far we are in terms of our research outputs, we have now, roughly speaking, reproduced two PRLs. I mean, it's not a joke. The computations that are involved are really, as you've seen, not taking a lot of effort. And the main difficulty here is the identification of what to search for. There's a question: do the finite size effects appear only because of the topological nature? Well, it's a bit vice versa, right? So in a thermodynamic limit, Majoranas must have exactly zero energy. And in a finite system, even though the wave functions of Majoranas are exponentially localized at either edge of the wire, the two wave functions do overlap. I'm going to actually also show the Majorana wave functions a bit later, and we are going to see what is happening. So oscillations are something additional, an imperfection on top of the topological nature. You also see something developing over here, and you see that the superconducting gap is shrinking with magnetic field, and that's the unfortunate truth of life. Superconductors and time reversal symmetry breaking do not naturally coexist. Here it is the spin-orbit coupling which is protecting the superconducting gap. If I reduce the spin-orbit coupling, I see that very soon there is almost no topological gap remaining at all, and the splitting between the Majoranas is nearly the same as the splitting. So there is there's almost no way to distinguish two overlapping Majoranas from propagating states above the bulk gap. All right, so this sets the stage. We know about Majoranas now, we know how to produce them. Let's now take a look at at the specialization of quant, and that is transport. But in order to deal with transport, we'll also need to think a little bit about the symmetries of the problem. So here we are having a Bogoliubov-de Gennes Hamiltonian, and it has the following set of symmetries. So it may have a following set of symmetries. First of all, there is the time reversal symmetry that flips the spin and applies the complex conjugation, which in turn applies complex conjugation to the momentum. So if I time reverse a Hamiltonian, that flips the sign of magnetic field, and it flips the sign of kx. Now, naturally, the Hamiltonian is invariant under time reversal symmetry only when magnetic field is 0. On the other hand, there is another symmetry which is present regardless of the parameter values. That's the particle hole symmetry. So that's I times the time reversal symmetry times tau y, where tau y is the second Pauli matrix in the Nambu space. So if I substitute, it's I sigma y tau y times complex conjugation. So particle hole symmetry always, when applied to a Hamiltonian, always gives the same Hamiltonian with the opposite sign. And it is indeed the particle hole symmetry that guarantees that if you have an isolated state at 0 energy, then no local perturbation can move the state up or down in energy. So in other words, this is the symmetry that guarantees protection of Majoranas. Now, of course, this is all in a single particle formalism, and the many-body equivalent of the particle hole symmetry is the Fermion parity conservation. Oh, I realize I closed the Q&A. Yeah, here it is. Yes. All right, so let's confirm that we've done everything correctly. Spoiler alert, if we did. And let's verify that our Hamiltonian does have all the symmetries. So here we're going to define Pauli matrices. These should be familiar. We're going to define the operators corresponding to particle hole symmetry, time reversal symmetry, and electron hole symmetry. This is not electron hole symmetry. This is the expectation value of a particle charge. This operator has a value of -1 for electrons and +1 for holes. And we are going to use to sort the eigenstates by eigenvalues of this operator to compute the conductance. That comes later. So now let's specify that these operators are indeed properties of the Hamiltonian. So we assign quant has bookkeeping for discrete symmetries. And here we assigned the specific forms of the operators to what quant in the proper way to our definition of the quant system. Now let's indeed check that these symmetries apply. So here we are going to set some parameters. And let's validate. Let's take the discrete symmetries and see if the Hamiltonian indeed has them. It's not a very exciting thing to do, but at least it tells us that we are doing things correctly. So we see that if magnetic field is 0, then no symmetries are broken. That's how to interpret this output. If we set a finite magnetic field, we see that the time reversal symmetry is now broken. That's what this validate function tells us. It returns the list of broken symmetries. Now it also returns a statement that the chiral symmetry is broken, which you could ask, what is this and why do we even have this? But whenever you have a particle-hole symmetry, which is anti-unitary, so it complex conjugates the Hamiltonian, and it's an anti-symmetry, it changes the Hamiltonian sign, and you in addition have an anti-unitary time reversal symmetry, their product is a unitary antisymmetry. So there is a unitary operator. Here it's just tau y that, when applied to a Hamiltonian, changes its sign. This one is broken whenever either of the particle hole or time reversal is broken, and therefore here it's broken as well. All right, so this is good. We verified that the Hamiltonian has the symmetries that we expected. Let's turn to conductance, and that's where the particle charge enters the picture. So when we compute the Andreev conductance, we need to send in electrons at at a certain energy. Some of these electrons may enter the superconductor as Cooper pairs and reflect back as holes. Holes carry the opposite charge. If the energy of the incoming electrons is sufficiently high to go above the superconducting gap, they enter the superconductor and do not return. So all in all, we need to compute this quantity. This is the conductance between a normal metal and a superconductor. There is a prefactor of E squared over H, that's the conductance quantum. Every incoming electron carries exactly a conductance quantum of current. The reflected holes, despite they go in the opposite way, because they have also the opposite charge, carry current with the same sign, whereas the reflected electrons carry current with the opposite sign. So this brings us to basically the definition of what we need to compute. We need to, first of all, solve a scattering problem. And then we need to compute how many electrons there are incoming. We need to compute all reflections, all transmission, all reflections of the holes, all reflections of the electrons, plug them into this expression, and we're done. So now, instead of a finite system, we are going to make a scattering system, which is, if you remember yesterday's lecture, a finite system with a couple of leads attached. So now we are going to make an interesting trick where the finite system is going to have exactly one site. And this is going to emulate a tunnel barrier. So here we are creating it. We make a quant builder once again. We fill it by using the template of the Hamiltonian that we used before. We replace delta with the delta of the normal lid that's going to be 0. And we substitute for the chemical potential a different value that belongs to the barrier. So this pattern of taking a template and substituting parameter values is useful when dealing with different parts of the system. Now, the shape of the barrier is just a single site at the origin, and that's it. To this barrier, we are going to attach a lead. So a lead is also a quant builder. Unlike a barrier, it also has a translational symmetry in the positive x direction. It also has particle hole symmetry and a conservation law. So these are the charge conservation law. These two are relevant to sort the incoming and outgoing modes according to and compute them in the proper basis. So now we once again fill the lead by using the original template, and we once again substitute the parameters by using the superconducting in the gap in the lead. That's going to be once again 0 because the lead is normal. And we introduce a new parameter to the problem, the chemical potential in the lead. We do the same thing with the topological lead. That one has a finite superconducting gap, and therefore it has no charge conservation. The electrons are coupled to holes. And now we are going to fill it by using the template, but that's the bulk of our system, and here we do not substitute any parameters. All right, finally we attach both. So the scattering region is just one site. We attach to it both leads, and we finalize it. That's what we. That's a function that's what we need to do in order to do calculations with a quant system. So we see indeed there's one site in the scattering region. This plot is extremely similar to what you saw yesterday. And there are two infinite leads attached to it. One is a probe, that's a normal metal. Another one is an infinite wire with induced superconductivity. This is where we are going to create the topological transition. So we now created the scattering system, but we are not yet ready to compute the conductance. That will still take some more work. So here we are going to compute the scattering matrix. Since we now defined all the full problem, we don't need to do anything else. We just provide all the necessary parameters. And previously, I have introduced the default parameters. Now I also specify a certain value for a barrier. And I can look at the scattering matrix, at the matrix elements in the scattering matrix. That's what they are. It doesn't tell us much, but first of all, you see that some of these entries are repeated. And that is indeed because Quant has already used the particle hole symmetry and the charge conservation in order to group these. So in fact, the different blocks, 2 by 2 blocks in the scattering matrix correspond to scattering between electrons and electrons, holes and electrons, etc. So here we are separating the scattering matrix into different blocks corresponding to different charges. And indeed, the scattering matrix between electrons and electrons is this sub-block of the full thing. Now, since we have specified the particle hole symmetry, we can confirm whether it is indeed present. And in scattering matrices, actually, discrete symmetries do not look exactly the same as the Hamiltonians, because scattering matrices are computed in the basis of propagating modes. So these are eigenstates of momentum. But in particular, particle hole symmetry means that the electron refraction matrix is a complex conjugate of a hole reflection matrix. So we can subtract these two to confirm it's indeed the case, and sure enough, we see that these two matrices are equal down to numerical precision. All right, so we have figured out how to compute a scattering matrix, how to separate it into different blocks according to the charge of the reflected particle. Now we are ready to define the Andreev conductance. So here we feed a scattering matrix. We compute the number of incoming modes. That's a size of a subblock of a scattering matrix. We compute the electron transmit, the amplitude of a normal reflection, the amplitude of the Andreev reflection. That's all the incoming electrons that got converted into holes. We apply the formula that we know from before. We combine these quantities in the appropriate way. Now I also introduced a convenience function that computes a conductance given a quant scattering system, the relevant energies, and the relevant parameter values. So now we are ready to do the calculation. I introduce another convenience function for plotting. This calculation is going to take a little bit more time because we need to solve a scattering problem each time. But let's take a look at what we obtain. And observe we are now slowly accumulating more parameters. Yeah, all right, that's slower, and I realize this is also required. Just a moment, let me rerun this. All right, so let's take a look at what we see. There's clearly a quantized peak, or a nearly quantized peak, but it's at the value of 4. And we have a zero magnetic field. So this is now a test value of parameters, a trivial system where all the chemical potentials are equal and equal to 0.5. There's a finite superconducting gap. We see the enhancement of conductance at low values of energy. This is because all incoming electrons, there's no barrier here. They cannot undergo a normal reflection, so all the incoming electrons get converted to holes. This phenomenon, conductance doubling compared to the normal state conductance, is a characteristic property of a transparent contact between a superconductor and a normal metal. Let's see what happens if we introduce a tunnel barrier between the two. So I don't know which value to use, but here I'm using a finite new barrier. And once again, it will take a moment for this to recompute. We see now that what are we seeing? Oh, what are we seeing along each axis? That's a great point. The vertical axis is conductance. Let me also label these. The horizontal axis is the energy. That's it. Thanks for the question. And the vertical axis is G in units of E square over H. Should I rerun this? Yeah, probably I should. All right, the calculation is, yeah. So now we see once we introduce the barrier, the conductance at zero energy is dropping. Let's make the barrier even a bit stronger, 0.5. So now we have introduced a tunnel barrier between normal probe and an electron and a superconducting lead, because the superconducting lead has a very low density of states. The conductance goes below the quantized value. However, due to the Van Hove singularities at the edges of the superconducting gap, we see relatively sharp peaks in the conductance. This is once again without magnetic field and in a trivial regime. Let us see what is going to happen if we try to observe Majoranas. So to do so, let's change the chemical potential in the system to be a bit lower, and let's introduce a finite magnetic field, so 0.4 or so. Now, this, of course, once again takes a bit of time to recompute. That seems to be still, no, all right. Hooray. That seems to be a fair bit more complicated, actually, probably because I used a huge magnetic field. Let me probably also reduce the chemical potential even further in the system. But we do see that there is now a quantized peak with a height of 2 e square over h. That is the quantization due to Majorana's. All the other stuff is due to different features of the band structure of the normal leads, which is also something tricky, and it takes quite a bit of parameter tuning to bring the system to a proper regime. So for now, we observe that the Majoranas do indeed provide a quantized conductance, but we observe that away from zero energy, quite a lot of other things are happening. And in view of the time, I'm not going to go into details about tuning things further. So let's see what we have done now. So we first discretized the continuum model. We applied the discrete symmetries. We have particle, hole, and charge conservation, and we observed a topological transition. Now, at this level, actually, there's probably hundreds and hundreds of theoretical papers that do not require a calculation that is more sophisticated than that. We could also right now take a scattering matrix and look at its determinant, which should change sign. But in view of the time, I'm going to show a couple of other points in Majorana physics and then conclude with questions. So first of all, I think this is still something visible in the plot I've shown before. If you're very careful, you will see something interesting happening in this plot. Namely, a couple of states are sticking below the rest of them, and this was something that was studied that was observed relatively early. Just a moment. By the group of Pete Brower, and then forgotten until people tried to understand whether quantized conductance is indeed a property, is indeed a clear signature of Majorana's. Long story short, people came up with people identified a concept of quasi-Majorana's. And that is related to what is happening when the chemical potential is not constant, but rather depends on the position. So here, with this small replacement, we are changing a constant chemical potential to a chemical potential that depends on position. So now, in order to specify I'm going to demonstrate what is happening, but in order to specify a particular shape of the potential, I'm going to introduce a smooth confining potential. So this is like a tunneling barrier that one usually seeks to create in a Majorana wire in order to implement a tunnel probe. But instead of being defined just as a single site, this one has a finite width. So it's this is the potential. It approaches a value away from the bump, and it has a finite bump located at the coordinate x0. So let's see how the spectrum of a Majorana wire looks like if instead of having a constant potential, we add this smooth potential, which is also going to indicate about how different it's going to be an illustration how different physical parameters interact with each other. So this part is very similar. Now there's a slight complication. Now, instead of providing a single value when we are evaluating the Hamiltonian, we are providing a complete function. But other than that, we are doing exactly what I described. We're supplying this position-dependent chemical potentials and looking at the spectrum of a Majorana nanowire. Let's see what we get. Yeah. All right. Okay. So far, there is no bump. The value at the barrier is exactly the same as in the nanowire itself. The system is just somewhat larger. So the width here is 20 sites, but otherwise it's a very similar system to what we had before. So let's see. We clearly see the same topological phase transition. There are two Majoranas. And now you see the same phenomenon as what I hinted at previously. Two states like to stick to zero even before the topological transition happens. Let's see how this phenomenon changes as we introduce a barrier. So we make a smoothly dropping chemical potential next to the edge. So I now make the potential change over a length scale of about 20 sites from 0 to 0.4. And lo and behold, so the topological transition didn't move. This is still the bulk thing. 20 sites is definitely a lot smaller than what is necessary in order to contain two Majoranas. But you see, there are two states coming to zero and sticking very close to zero. In fact, they stick even better at zero than the Majoranas in the topological regime. That was quite a bit of a surprise when people started studying it. Turns out there's a semi-classical argument, and there is a different exponentially protected degeneracy of states that appears when the confinement is smooth compared to the spin-orbit length scale. So in order to confirm what is happening with the states, let's take a look at the single wave functions. So here I'm going to get a Hamiltonian of this finite wire as a matrix. I provide all the parameters, and I'm going to diagonalize this matrix and look at the eigenvalues and look at the eigenvalues and the eigenvectors. This is, let's see, so here Bx is 0.5, so this is about here. We are in this regime. The rest of the parameters are the same. The confinement is now sharp. So the value of the barrier is the same as the value at the barrier is the same. What we see now is two Majorana wave functions that are localized. They are hybridized and therefore overlapping. Now you also notice there's a lot of wiggling. Now that is because we are plotting really the eigenvectors. However, remember that on each side we have 4 degrees of freedom, 2 spins and two number degrees of freedom. And actually I should probably, and here I'm plotting the eigenvectors, so it's just discarding the imaginary part. So in order to combine this, I'm going to compute a wave function density. I have introduced an operator that basically sums all the orbitals belonging to the same site. Density. And we do see 2 exponentially decaying wave functions. That is as expected for the Majoranas. The decay, however, while the decay is exponential, it still does not, the 2 wave functions do not quite drop to 0. And that is because the finite. So this is exactly, these are exactly this finite size effects you were asking about before. If the nanowire is not long enough, there is a finite overlap and a finite splitting between Majoranas, which is also not so definitely not something we want because this interferes with quantum computing. All right. So now let's introduce a barrier. Let me see. 0.1. Just a moment. No. Oh, of course, I should also. So what the magnetic field here is still in the topological regime. Let me see. I need to take a magnetic field that is before the topological transition. So in the trivial regime, and that's about like 0.3, 0.25. So let's take a look at the wave functions in this regime. Ha! So we see that this wave function that has, I remind you, an energy that's basically that's actually smaller than the energy of the two Majoranas. It's entirely localized on one edge of the system, so it is protected by a different mechanism. Now, I really won't have time to go into this, but turns out these wave functions also, these quasi-Majorana states can also give a quantized conductance, and therefore that's why one needs to be really careful with claiming that quantized conductance means that there are Majoranas. All right, now I really have only a couple of minutes remaining. So as a final example, let me quickly demonstrate a problem. And for the solution, you'll have to look at the notebook on your own later. That's going to be homework. I'm going to do the same thing, but I am now going to study proximity superconductivity. So I'm going to go from purely one-dimensional systems to two-dimensional systems, and I'm going to see how the physics changes. What I've done is essentially the same as before, but I have now introduced the terms in the dispersion relation that are related to movement in the transverse direction. I now created a template corresponding to a superconductor. That's the normal dispersion plus superconducting pairing. And then template corresponding to the normal dispersion plus the Zeeman field. This is going to be a semiconductor. Now, very similar to what I've done before, I'm going to create an infinite translational invariant system that I'm going to make 10 sides belonging to a superconductor and 10 sides belonging to a semiconductor. I'm also going to plot it. So this is now a finite wire infinitely extending in the x direction. So it's a wire with a finite thickness, but translationally invariant in x direction. Let's look at how its dispersion looks like. So this, of course, now the system is much larger, and actually before long, if you just add dimensionalities as quickly as that, you run out of computational power because you add more and more orbitals and more degrees of freedom. That's when numerical efficiency starts becoming important. So let's try and interpret what we see. We see that the magnetic field is absent. We are looking at the normal dispersion relation. The superconducting pairing is 0.2. That's over here. This is, once again, we are looking at the band structure. But we see that there are states with everything is still gap. There's induced superconducting gap, but the superconducting gap is much lower than the original bulk gap. Now let's see if we can induce a topological phase transition in this Hamiltonian. And we can indeed try. So these states are probably mainly in the normal region because their energy is much lower than the bulk superconducting gap. So indeed, if we increase the superconducting, increase the Zeeman field to some finite value, we are going to rearrange this band structure. I'm not sure if this is too large. This is probably already too large. Yeah, so here we are at the topological transition. So in other words, we still are able, we have now tried to simulate how the same system would look like if we remember that the wire is really two-dimensional instead of being purely one-dimensional. We observe that we can still introduce a topological transition. However, the dispersion relation doesn't look like anything we've seen in a simple one-dimensional model. And now this certainly came as a surprise to me when I was learning about this. But in fact, the phenomenon that we are observing is known since the 60s and since the works of Dejean, who was studying superconducting vortices. Specifically, the trajectories that go along that go in the normal part and propagate almost parallel to the interface between a superconductor and a semiconductor. These trajectories almost never see the superconducting gap. So the time it takes for these trajectories to encounter a superconductor is very long. So let's see, these are trajectories with a large momentum parallel to the x direction. So these are indeed the ones that are flying along the wire. And these trajectories are the ones that due to which the superconducting gap is suppressed. Now that's actually something that I already advertised a bit last time. But a master student in Delft, when he was so he was learning about this problem and said, "Oh, that's bad. Why don't we make the system like this? Why don't we turn it into a zigzag?" Well, that does remove these long-running trajectories and should solve the problem. So turns out that does work. And here I wrote some code that should allow to demonstrate this. I now create a system with a supercell where half is still superconductor, half is a semiconductor. But in view of the time, I think I should really wrap up here. And I hopefully, if the organizers allow us, still have a minute for questions. But otherwise, I would thank you for your attention.
Thank you, Anton. You are allowed to have a minute for questions. Any question? No? Last chance? Okay. Otherwise, there is the Slack channel and you can write your questions there.
Yep, that's right. So if
you
have any follow-up questions, do write in Slack.
Yeah. Otherwise, since we are a bit late, let's go for Christiane.
Yeah,
hello,
thanks
Christiane.
Everyone.
So the next talk will be given by Christiane Moraes-Smith. And Christiane, whenever you want.
Yeah, I am almost ready. Let me share. Start. Do you see my slide?
Yes.
Yes, you hear me well?
Yes.
Okay, very good. So good afternoon, everybody. It's a pleasure to be back today to continue a little bit with the thermodynamic description of topological insulators. So before yesterday, we were looking at the most common models studied, and we have seen that we could describe topological phase transitions as a thermodynamic phase transition. And today we are going to concentrate on two other examples, which are a bit more intricate. One are higher order topological insulators and no-Hermitian topological insulators. Okay, so just to recall very fast what we talked about on Wednesday, we said that the field of topological insulators has been developing based on classifications based on dimension and symmetries. And out of that, we could predict how should be the topological invariant for each topological phase in different dimensions. And we wanted to take a completely different approach and try to understand whether we could do the same and predict these topological phase transitions using a thermodynamic approach. We had two problems. One is that the system is finite. So what is the meaning of thermodynamic limit? And because of that, we were inspired by the so-called Hill nanothermodynamics that allows us to treat finite size systems. And today, as I said, we are going to generalize the things we did from Hermitian systems to the non-Hermitian case. Oops, why it's not going? Yeah. So if you remember, the second problem that we had, besides the fact that our systems had boundaries and everything interesting is happening at the boundaries, so we couldn't go completely into the thermodynamic limit, there was another problem when we tried to describe topological phase transitions, is that at these phase transitions, there is no symmetry breaking, so we can't apply anything like Ginzburg-Landau formalism, and that we have a completely delocalized order parameter. But as you recall, the Ehrenfest classification still holds, and I have shown to you that we can describe them using that. And the Ehrenfest classification is nothing but looking at the nth derivative of the Gibbs free energy, first, second, third, and so on, and looking which is the number of the derivative that shows a discontinuity or a divergence. And that number decides the order of the phase transition that we are going to have. So today we will now do the same for the Hotchkiss and for the non-Hermitian TIs, as simple as possible, just to illustrate the problem. So just to recall, I think you have been learning what higher order topological insulators are. These are the Hotchkiss. The usual topological insulators have a bulk in G dimensions, and they will show topological properties at the edge that has dimension D-1. On the other hand, these higher order topological insulators, they have a bulk in D dimensions, and they will show topological properties that appear in dimensions which are smaller than D-1, at least D-2. So simple examples would be that, for instance, in 2 dimensions, as you see here in D, instead of having the edge modes that are 1-dimensional as in C, where you have in a chaired insulator, you would have corner modes, characteristic of a quadrupolar order. And in 3 dimensions, you could have either 1-dimensional hinge states, or you could have corner modes again. So it has to be D-2. These models were proposed by Ben Alcazar, Bernevig, and Taylor Hughes in 2017, and that's the model that we are going to use today. These models have been observed experimentally in many different systems, in bismuth and in metamaterials, some of them made with photonic systems. You can see here some Kagome lattices, but also in electronic systems. We did it in 2019, an artificial electronic quantum simulator where we could see the corner modes. So these systems didn't have all the features of the original BBH model, but they have lower dimensional corner modes in a 2-dimensional lattice. Generic in that sense. Okay, so let's then now concentrate on the paradigmatic model for Hotchkiss, which is the BBH model, which now consists of a 2-dimensional lattice with hopping parameters gamma x and lambda x, so like the 1G SSH model, with the difference is that now along the vertical direction, I don't get gamma y and gamma y, but here it's minus gamma y, which means that there is a flux piercing my plaquette. Okay, so this inversion of the hopping parameter, it's something that is not very obvious to realize experimentally because you need a flux, but it's possible to do. And then it's simply a model with alternating hopping in the x direction, gamma x, lambda x, and in the y direction, minus gamma y, minus lambda y, but this becomes positive in the next vertical. Okay, that is then the Hamiltonian of the model, a simple tight binding Hamiltonian. And it was shown in this paper that this model has very interesting phases. if I look at a phase diagram in terms of gamma y over lambda y versus gamma x over lambda x. And these phases are characterized by the polarization, which is now a vector, px, py. And we are going to have many different phases. So one where the polarization vector, px and py, are both 0. So we are combining the plaquettes in that way. And this is then the trivial phase, which is represented here by the red dot. There is then another phase in which I will get here a dipolar, but just for one of the py, let's say, and not for the px. So my quantum number here, my topological invariant is 1/2 and 0. This is the so-called dipolar phase, and the plaquettes are closed along the other direction. But we could also then have another phase, which is the quadrupolar phase where we have a corner mode completely isolated in the n directions. And here you can see your corner mode in this plot. So this is a very rich phase diagram with now 3 different phases, not just trivial and dipolar or trivial and quadrupolar, but with all the 3. And the question now that I would like to address is, am I able to describe these topological phase transitions in this more complex system, also using the thermodynamic description? Okay, so let's first concentrate in the simplest case, which is along the diagonal when gamma x is equal to gamma y. And then, so gamma x over lambda x is equal to gamma y over lambda y, and we'll call this just gamma. And in this case, we are just looking at the transition between the quadrupolar and the trivial phase. Very good. Let me then just recall with you how is the energy spectrum as a function of gamma for gamma x equal gamma y. And we see that we have here a 0 mode between -1 and 1, which means when I am in the quadrupolar phase, and just a gap opening for the trivial phase and nothing else. And this quadrupolar phase, you can see here when you have the px and the py converging to give me the red and the blue corner modes. These are these protected modes. So before we do the calculations for this case, let me recall briefly with you what I explained on Wednesday when we tried to do a thermodynamic description of topological systems for which we have a Hamiltonian. We are going to do 2 things. One is to determine the ground potential given by the log of the trace of h minus beta h minus mu n. That's the usual thermodynamic relation. And then we are doing this ansatz that our ground potential can be separated into 2 parts, and this is inspired on Hill thermodynamics. That was possible because we did not assume all the quantities to be extensive. And then we can have one term that is extensive, which is the bulk term times the volume, and another term that's non-extensive, like the surface times the area, for instance. And in 1 dimension, this would simplify that my bulk is multiplied by the length, and the non-extensive part would be just the corner that does not depend on the length scale, right? And if we look now at the quantum phase transition itself, this is going to be complementary to the notion of topological invariance. So one of the examples that's going to be useful also to compare later with the non-Hermitian case is the SSH model. I have a 1-dimensional chain with a hopping T and T2. And now I am going to look at the phase diagram energy, first at the spectrum energy versus T in unities of T2. And I will see that for T smaller than T2, from between modulus of T smaller than T2, between -1 and 1, I have a 0 mode here at the boundaries, and for T over T2 larger than 1, I don't. So there is a transition from a topological to a trivial phase, right? And when I now do the calculations, either by solving the problem for several length scales and separating the extensive part of the free energy from the non-extensive part. So this is the boundary, this is the bulk. I can now start taking derivatives according to the Ehrenfest classification, and I will immediately see that the non-extensive part, which means the boundary, is going to have a phase transition because it has a discontinuity precisely when t is equal to t2. It's the first order phase transition, is the first derivative, whereas for the bulk, which is in red, I am going to have a second order phase transition precisely at the same point. It's the same point where we knew that the topological invariant was changing. So both phase transitions at the bulk and at the edge, they occur at the same point, but they have different orders, okay? So this is a discontinuous and this is a continuous phase transition. That's what we have seen last Wednesday. We understood also this in terms of the Josephson hyperscaling relation that tells me that the order of a quantum phase transition is connected to critical exponents nu and z. And this is the codimension of my system, G. And these exponents nu and z are determined when I look at how my gap closes as a function of two parameters. One is the external parameter that I'm tuning to drive my phase transition. Here is the hopping, but it could be anything else. So how far I am from the critical hopping parameter at which I have the phase transition. And P is just how far I am from the critical momentum at which I drive the phase transition. So if I look at how my gap closes for the parameter equal to 0 as a function of momentum, this exponent tells me this critical exponent z. And if I look how the gap closes as a function of this g parameter at 0 momentum, I will get that this is nu z, and since I have z from here, I can get nu from there. And what we have seen then, it's for the SSH model, for the Kita F chain in one dimension both, for the two-dimensional models, Kenny-Milley and BHZ, and for the BHZ in 3 dimensions, all these systems belong to the same universality class. They all had nu equal 1, z equal 1, and the order of the phase transition is always the codimension plus 1. And one can then show that they belong to the Dirac universality class. That's what Rodrigo Aroca has shown this year. So I mentioned it, but I didn't show you, and this was an example for the Kita F chain that we could use these topological states to build, for instance, a heat engine. And then I would have the best rendement for my heat engine if I would operate my system close to the phase transition. That's the best point. And I would have my edge and my bulk behaving differently. One would be like a refrigerator, the other would be like a heater. This has been published in collaboration with a group of Özgür, Mr. Caprioglu, this last year. Okay. So now I want to go and look at the hotches, because this is now a more complex system where I would look, for instance, in 2 dimensions. I don't have only the bulk that's scaling with the area. I also have the edge that's scaling with the length, but I have the corner that is scaling without any dimension, right? So now the question is, could I try to describe, using the same approach, this kind of systems? So we have seen that we could do this in 2 ways, either by using the Hamiltonian, calculating the ground potential and doing a scaling relation. This was one possibility to separate these contributions. But we could also use correlation functions. And I have shown you that if we use correlation functions and look directly at derivatives of omega with respect to any parameter, I would do a much faster job by calculating correlation functions. So that's what we are going to do here, because this is really a regime when this would be very costly to do, this scaling approach. So now, let's do them, since we were first looking at this phase transition from the trivial to the quadrupolar phase when gamma x equal gamma y is equal to y. we will then use the Hamiltonian. We will need to calculate all these correlation functions to calculate how is the derivative of my free energy at zero temperature with respect to some parameter that I'm tuning. And when we do that, we will now use the same kind of approach that we used before, but now it's slightly more intricate. Because suppose that I want to calculate the variation of the omega at the edge. So I want to get the red and the blue parts. Before, since I had only edge and bulk, I could calculate the problem for periodic boundary conditions on the torus that I had then the system for the bulk, and I would subtract the closed, the open surface from that. I would immediately get the edge. But now I also have corners, so the problem is a bit more complicated. So if I would like to get the edge, what I will do is I will calculate the problem when I have periodic boundary conditions only in Y, plus the problem when I have periodic boundary conditions only in X. And now I have to subtract one bulk to have just the edge here. But here I have been adding the two bulks. So I have to subtract these two bulks that I added here. So twice the calculations on the torus to be able to get just the remaining blue and red parts. And if I am going to calculate how the corner behaves, the derivative of the corner with respect to some tuning parameter, now I want the dots. So to get the dots, I have to start by solving the problem for an open configuration in 2D. Now I have to get rid of the two red, so I have to subtract the system with partially open, periodic in one direction, boundary conditions. I have to subtract the two blue. I have to take periodic conditions now along the X direction. But now look, I had one bulk, I subtracted one bulk, but I still subtracted another bulk while doing this one. So I have to add one more full bulk to get rid completely of the bulk and get only the 4 dots there. So we are then going to calculate these correlation functions for all these configurations. And we look first at the spectrum for these configurations here. And what we see is that when I have an open boundary condition, I am seeing the closure of the gap and these zero modes in this regime between -1 and 1. When I have the torus, I close the gap, but I don't have the zero modes because the system is periodic. And I can also close the gap when I have partially periodic boundary conditions. So this is solved by gamma x equal gamma y equal to gamma when I am along that diagonal in the phase diagram. And if I now do my calculations by taking the thermodynamic potential omega and taking the derivatives with respect to gamma, that is equal to gamma x and gamma y, I will then see that I am plotting in different corners. Omega corner is in green, omega edge is in yellow, omega bulk is in blue. And now I take first, second, and third derivatives, and I immediately see that the corner has a spike for the first derivative, the edge has a spike. You see here, there is no spike. The edge has a spike in the second derivative, and the bulk has a spike in the third derivative. So this gives me precisely the same thing I had before. I can go now and look at how the gap is closing, and I'm going to find that Z is 1, mu is 1, and the transition between the trivial and quadrupolar phases belongs to the same Dirac universality class with the same critical exponents as before. Okay, easy and nice, but in addition to that phase transition from the quadrupolar to the trivial phase, so where we went along this line where the symmetries were preserved, I can also have other topological phase transitions. For instance, this one in blue from the dipolar to the quadrupolar phase, or this one in green from the trivial to the dipolar phase. Is this thermodynamic description of topological phase transitions going to hold also here or not? Let's now see what happens if I repeat the same procedure. The only difference is that along the red line, I had gamma x equal gamma y equal to gamma. And now here, I will plot for the blue one, I will use gamma x equal to 0.5, and I will plot things as a function of gamma y. That's now my x-axis here. And for the green one, I will again have gamma x equal to 1.5, because this was 1, this point is 1.5, this is 0.5, the 0 is at here at the center. So I will solve the problem for different values of gamma x, and I will plot it as a function of gamma y. Okay? And now my color codes here means that red is this transition, blue is this transition, and green is this transition for different values of gamma x. And now I will plot only the parts which are the most interesting, because you don't need to look at everything. But here I already see something quite different. So look first at the red ones, the quadrupolar to trivial, that one we have already analyzed. At the corner, I am going to see a peak at the first derivative. At the edge, I see a peak in the second derivative. At the bulk, I see a peak in the third derivative. That's what I have shown you in the previous slide. Everything is fine. But now, look at the blue, the transition from the dipolar to the quadrupolar. I see a discontinuity for the corner. I see a peak for the edge. So I am capturing the phase transition for the corner or for the edge. But for the bulk, I see nothing, just 0. I can't capture the phase transition at the bulk for this phase transition. And now look at that one between the trivial and the dipolar in green. For the corner, 0. For the edge, 0. For the bulk, 0. I cannot capture at all the transition from the trivial to the dipolar phase in terms of the thermodynamic variables. So what's going on? Could I interpret all the other phase transitions as quantum phase transitions, these topological phase transitions, and now not anymore? How is it? So let's look at the spectrum to try to understand what's going on. So when I look at the spectrum for the dipolar to the quadrupolar phase transition at gamma x equal to 0.5, look at what I see. If I have the corners, I see the 0 mode and I see a gap closing. If I have my cylinder and I plotting things in terms of gamma y, I see a gap closing. Those were the two that I could describe in terms of the thermodynamics. But if I have a bulk, if I have a torus, so I'm looking at the bulk, there is no gap closing. So it looks like, and here also there is no gap closing in terms of gamma x. So it looks like that if I have no gap closing, I cannot see it with the thermodynamic variables. Look now at the transition from the trivial to the dipolar. Nothing, no gap closing at all. So it is a completely different type of phase transition. Doesn't occur due to a gap closing and the appearance of the 0 modes, right? Because it's based on a different symmetry. These are these topological crystalline insulators. And then I am no longer able to capture with the thermodynamic formalism. But this was known from the work of Benalcazar in 2017, that there is no gap closing for some types of boundary conditions. But in that work, he also gave us the solution, what we should do to understand all that. And the solution was to look at the so-called Wannier spectrum, because in terms of the Wannier spectrum, there is always a gap closing. So what we will now look at this Vanier spectrum and see whether we can use it to do some thermodynamics. So in that way, we are going to define something which is called a Vanier grand potential. So if you take your Wilson loop, which is defined in terms of the Vanier Hamiltonian, and the Vanier Hamiltonian has eigenvalues, which are these Vanier centers, I can now define my Vanier grand potential in terms of the sum of these Vanier centers, which are below, smaller or equal than mu, where mu is now this Vanier chemical potential. And now, for this Vanier grand potential, I can apply the same kind of approach where, because now this Vanier grand potential is something that is happening at the boundaries, okay? So since it's something happening at the boundaries, the bulk is now for a one-dimensional system times the length, and the edge is a zero-dimensional system. And if now for this Vanier grand potential, I separate the part that it's extensive and non-extensive, and I take derivatives, I will immediately see that the first derivative of the edge shows a discontinuity and the second of the bulk shows a discontinuity. The same for the blue, this is for the red transition when gamma x equal gamma y, so from the trivial to quadrupolar. I will see precisely the same for the dipolar to the quadrupolar, so the edge is first order and the bulk is second order, and I will see the same from the trivial to the dipolar when I am now at 1.5 for gamma x. So if I enlarge my definition of thermodynamic potential and I include the Vanier grand potential, I can again visualize the topological phase transitions and understand them in terms of quantum phase transitions, because now the gap is closing for everybody. Okay, so very nice. It seems to work, but I need to have some features in the spectrum such that I could use these definitions. Okay, I can now then come to my partial conclusions for the first part of the talk about the higher order topological insulators. So we can use a thermodynamic approach to characterize the quadrupolar to trivial phase transition. And if there is a gap closing, the topological quantum phase transitions leads to this thermodynamic phase transition, and this will respect the Josephson hyperscaling relations. But there are some transitions that are without any thermodynamic response. And to explore those, we have to use Wilson loops and the Vanier spectrum. And then when I do that, I find that they are also in the Dirac universality class. And the main message from this part is to get higher order, use Vanier. I see that there is a question, please. Should I read the question or is?
Yes, please, because we are streaming on YouTube. So like this, they can hear it.
Okay, so I should read or do you read, Maya?
Okay, I read it. How is this Vanier Hamiltonian defined?
I have it at the very end. Okay, may I ask you to let it to the very end because it's my very last slide. So I come back to the question when I finish the talk, if you agree. Okay, it's defined in terms of the Wilson loop, but I can show you the calculations a bit more in detail, but it's my very last slide after the end of the talk. So I show you at the very end, if you allow me. Is there any other question? Okay,
no,
so
that's it.
Yes. So then let me go to the second part of the talk, where now I would like to talk about the non-Hermitian models. So until now, we had these topological phases that were in the universality class of the Dirac model. And what happens now if we go to these more complex non-Hermitian models? So now it's very different, because non-Hermitian means that the Hamiltonian is different from the complex conjugate, and now my energies became complex. And it's such that my Hamiltonian applied on a certain state psi with what we call a right, will have an eigenvalue, which is the energy E. But when I apply psi daga on the psi left, I will get my E star. So the system became much more complex. And what happens is that now psi right is no longer a delta, who is a delta Mn now is the sandwich between the psi left and the psi right. So things can be cast into what we know, but we need to use this biorthogonal quantum mechanics, where the states are now to the right and to the left, they are different states. When I have to calculate correlation functions or anything that means averaging, I need to use this type of left and right states. So there is also one interesting thing, because the periodic and the bulk are very different. So I am going to have a completely different spectrum for open and periodic systems. And when I have an open system, it's not that I am getting just what I had for the bulk plus my corner states. It's much more complicated. And I am going to show you that in this case, we can use a very beautiful concept, which is called the surrogate Hamiltonian. So if I have an open system and I now do an analytical continuation of momentum into the imaginary axis to k plus I kappa, and now I write a Hamiltonian, which is the so-called surrogate Hamiltonian in terms of this complex momentum, I am able to get for these closed boundary conditions precisely the Hamiltonian that I have for the open boundary conditions, just without the boundary modes. So the case here is going to be slightly more complicated, and these non-Hermitian systems, they exhibit a fascinating effect, which is the non-Hermitian skin effect, where we get accumulation at the boundaries when we have open boundary conditions. If I have a system which is non-reciprocal and it is easier to hop in one direction, the electrons are going to accumulate at one corner of my system. Okay, and this is again a very interesting feature of these non-Hermitian Hamiltonians. Okay, so where does it appear? Where do I get some non-Hermitian Hamiltonian? To get this, I need to have imaginary terms. So this usually appears, and we never think of it in that way, in any interacting systems. When I describe things in terms of quasi-particles and I get a self-energy, I get an imaginary part there, which is connected to the lifetime of my quasi-particles. This means that my energies are becoming complex, right? Because it's not infinitely lived, but finitely lived. But we can also construct non-reciprocal systems, and these non-reciprocal systems, we can immediately get energies which are complex, and where the Hamiltonian then is not going to be H12 is different from the H21. So the system is now non-Hermitian. Oops. What will happen is that in terms of the classification of the topological phases, this becomes much more complicated. This has been done. I refer you to those papers to look at the classification, and I want to focus here on the thermodynamics. So to just try to set the problem, I will look at the simplest possible case, which is a Suschriff-Heeger model, but which is now non-Hermitian. And if I take this one-dimensional model and try to make it non-Hermitian, so instead of hopping T and T2, now I have two options. One is to make these hoppings complex, such that, let's say I would have T e2 I theta to go here and T E2 I theta instead of minus I theta when it comes back, which means making my hopping complex. But those ones don't obey certain symmetries and they don't show this very interesting accumulation of modes at the edges. So I am going to consider one different type of model, which is just a model that has real hopping, but non-reciprocal, which means when I hop from B to A, my hopping parameter is real, but it is T plus delta. And when I hop from A to B, it's T minus delta, okay? So if delta would be 0, I would have the Hermitian case, but now it is easier to go to the left than it is to go to the right because the hopping is different in the two directions. So I write then the non-Hermitian Suschriff-Higger Hamiltonian. It's just a hopping Hamiltonian, a tight binding one, very easy. And this is the so-called non-reciprocal version. And now, as a function of T and delta, always written in unities of T2, we are going to have different phases. And the system is going to have a completely different phase diagram for different boundary conditions. So let's first then look at the energies. For the non-Hermitian SSH, if I write my Hamiltonian as a d dot sigma, we are going to see that we have winding around exceptional points. And the exceptional point that was before at 0 for the Hermitian case splits into this red and this blue exceptional points here, given when the real part of dx is equal to plus minus imaginary of dy, and the real of dy is plus minus imaginary of dx. And now my phase diagram in terms of the hopping t versus delta, delta is the non-Hermitian parameter, if you remember, in unities of T2 equal 1, is going to have several different phases. So look here when I go across this line, and we are going to see all the different phases in terms of the winding numbers. If I am here, this is A. I have a winding which is not enclosing neither the blue nor the red, and both of these winding numbers are 0. If I am at this point, now I am encircling one of the singular points, but not the other. I have 0 and then 1/2 for the winding numbers. If I am encircling both, I have 1/2 and 1/2. And now I go into the point when these two singularities are going to merge at 0. And then at this point, I recover the Hermitian case. It's the point where delta is equal to 0. And then they split again. I am at this point. I still am in the phase 1/2, 1/2. And then I go into the phase 1/2 is in 0, where now I am encircling the blue singularity, but not the red, and 0, 0 when I'm not encircling any of them. Okay, so I have all this sequence of phases, and that phase here was the Hermitian topological phase, and this was the Hermitian up here, the Hermitian 0. And now in addition, I have those ones that are non-Hermitian. Yes, there is a question, please. Do you read it, Maya?
Yes. What defines exceptional points?
Yes, so the exceptional points are the points at which I have these singularities. Before I had the singularity at the 0, and that's when I was calculating the winding. If I encircle the 0 for the trivial, for the normal SSH model, I would have that my winding number is 1 and I am in the topological phase. And if I don't encircle it, I would have the trivial phase. And now, because I now have real and imaginary parts for these exceptional points at which I have the singularity, these points have split into 2. Okay? So now I will look what happens. Is it clear? I hope. If it's not, please ask whatever again. So now I will calculate the spectrum when I have open boundary conditions instead of the periodic boundary conditions as I had here. If I have open boundary conditions, now I look at the real part of the energy as a function of delta. Delta is always the parameter that's giving me the non-hermeticity. And I will look first here what happens for periodic boundary conditions on the upper line and for the open boundary conditions on the lower line. The first plot is for the real part of the energy here and here. The second plot is for the imaginary part of the energy. And the third is for the absolute value of the energy. Okay? So what you can see here is that for the real part of the energy as a function of delta, you are seeing that there is some kind of folding around 2 here at 1 point something. For the imaginary, I had a gap in this part, and then this gap is closing at this point. And from the absolute value, I see that precisely at this point where the gap was closing, I see a spike there. If I now look for the open boundary conditions, I see something extremely interesting. So you see, for the small values of delta here, starting from delta equals 0, there was a gap. Then my gap has closed. I see a 0 mode appearing in this interval. And then the 0 mode, there is a set of bands here. But I see also something very interesting there. In addition to the 0 mode, I see that there are points here, up and down, where there is a collapse of all the bands. So if you think you are talking about fermions, suddenly I have a certain energy and all my fermions have the same energy. It's like for a flat band. I have this non-Bloch band collapse. These are very interesting points. It's the equivalent of Bose-Einstein condensation, but for fermions. All my fermions are going into the same energy state. It's a very funny point. I also see here for the open boundary conditions that I have here a 0 energy, and then suddenly I start opening for several values. So, and this is happening precisely at the point 1 point something where I was getting this collapse of all the energy bands. And this I can see also in the absolute value at this point there. So the spectrum for open boundary conditions is very rich. The real and the imaginary parts are complementary to each other. They are different, but they can see similar things happening. And now I can try to calculate what's the so-called surrogate Hamiltonian. So I make my K, I make an analytical continuation for my K, where this kappa is defined in terms of T plus delta over T minus delta and log of that. And now I can then see that for the surrogate Hamiltonian, I see the similar behavior as I had for the open boundary conditions, with the difference that here I am not seeing the 0 mode that I can see for the open boundary conditions. So the system with closed boundary conditions that I had been showing to you before, periodic boundary conditions, has a completely different spectrum than the one for the open. But if I calculate the surrogate Hamiltonian in terms of the complex K, then I get the same as for the open, except for the boundary modes, for the 0 mode here, as we were used to get, okay? This is good to keep in mind. And this is now the phase diagram that was known from the Kawabata paper, T versus delta. This should be a topological phase with the winding number 1, and this should be 0. So Rodrigo has been, and these are the points of the non-Bloch band collapse that I have been telling you, that all the states have the same energy. So Rodrigo has been recalculating the Kawabata phase diagram, and we have a much more detailed and precise phase diagram here. And now you can see that if delta is 0, where we had the Hermitian trivial phase and topological phase, what happens now is that even for delta non-zero, 1, and so on, in this regime, we get a phase that is connected to the Hermitian trivial phase, and here also a phase that's connected to the Hermitian topological phase. But now there are more interesting phases, which is this non-Hermitian trivial and this non-Hermitian topological phases. And if we now fix ourselves to be here at this value 1.1 for the value of t over to t2, and if we now look at the positive values of delta, because the same happens for the negative, we are going to have one phase transition, another phase transition, and a third phase transition. So there are 3 interesting phase transitions. One, which is between the Hermitian trivial and the Hermitian topological one. We could imagine what should be happening here. This is a very interesting point because it's the point at which we have this non-Bloch band collapse is along these 2 transverse lines, bringing us into the orange region. And this point here is fully between non-trivial topological, non-Hermitian trivial and non-Hermitian topological. And this is a completely new behavior also. And the question is, we probably should expect our thermodynamic description to hold here. What happens at the orange one here and at the transition between the orange and the green? So let's now think in terms of thermodynamics for non-Hermitian systems, and you will tell me, what are you talking about? Non-Hermitian systems, if the Hamiltonian is not equal to its complex conjugate, this is usually describing open systems. But if it's an open system, it's not even in thermal equilibrium. How do you want to talk about thermodynamics? What does this mean to start with? And well, it's true and it's difficult, but symmetries will save our lives. And there are 2 cases which are very interesting to consider. One is the case when our Hamiltonian has what is called a pseudo-Hermitian symmetry. And now what happens is that in this case, the energies come in complex conjugated pairs. So when I sum over all of them, my partition function is still real. So I am in business. And the other case that is also quite nice is when I have parity time symmetry, because in this case, the energies are already completely real. So for these 2 kinds of cases, when I have this type of symmetries, I am in business because my partition function Z, my thermodynamic potential is going to be real. And I expect that things that I know from thermodynamics should hold. Let's see if this is true. So now we will look at things at 0 temperature and calculate the sum of the energies. But now these energies are going to be complex, right? So I could even have a complex mu, and these energies are now complex, and the sum of them is going to give me my thermodynamic potential. But I have to remember that I cannot use regular thermodynamics. I have to use what is called the biorthogonal thermodynamics, because now my delta Mn is not the overlap of psi right with psi right or psi left with psi left, but the overlap between psi left and psi right. Okay? And we also have the problem that the thermodynamic limit could be well defined for open boundaries, because the system becomes unstable when I have an open system and I make it larger and larger. So let's start with the case of periodic boundary conditions when we have this phase diagram, and we will look again at the energies. I know that I have a gap opening here in this regime for delta is smaller than 0.5 in the real axis. In the imaginary axis, I have a gap opening for delta larger than 1.5. So I would expect that I would get phase transitions every time when my gap is closing in the real and in the imaginary axis. And if I now take the bulk, the omega bulk, and I take derivatives with respect to delta, I will see a spike at 0.5 where the real gap is closing, and at 1.5 where the imaginary gap is closing. And now I take the second derivative and I see a very clear spike. So it looks like my derivative of my free energy, as I did before, is capturing these phase transitions. But now when I look at it, I say, this looks kind of odd, right? This is a true spike in the second derivative, but is this a spike or not? Doesn't look so clear, right? Before I didn't have something, either I have a very clearly well-defined spike. Here you say, doesn't look so nice. Let's look at the scaling and at the critical exponents to be sure about it. So now when we look at how the gap is closing and we do the scaling analysis, you remember, I will look how my thermodynamic potential is going to scale as a function of G at zero momentum. And what I will see now, I will first of all see that my critical exponent Z, when I do this scaling for many orders of magnitude, how the gap is closing as a function of momentum. By taking my G equals 0, I find that my critical exponent is no longer 1, but it's 1/2. So the real part goes with modulus P to 1/2, the imaginary goes with modulus P to 1/2, and the modulus also does. And now when I look, how is my new Z by taking momentum 0 and seeing how my delta scales as a function of G, new Z is 1/2, which means new is 1. So instead of having the critical exponents 1 and 1, now I have them to be 1 and 1/2. And when I put them into the Josephson hyperscaling relation, it means that the order of my phase transition is 1.5. That's why when I looked at 1 here, at the first derivative, I was not so sure that whether I had really a phase transition or not. I should have looked at a fractional derivative with order 1.5. I will tell you something about fractional derivatives if you ask me a question when I come at the end. Okay? So we have now a different critical exponent, which is this 1/2 for the Z. It's already something different. There is also something more interesting that Rodrigo has been showing here in this paper, is that now the universality class that I have, it's the non-Hermitian Dirac model universality class, where this beta and this alpha are non-Hermitian. So before I had everything belonging to the Hermitian Dirac universality class, now it belongs to the non-Hermitian Dirac universality class, okay? And I can still understand the phase transition in terms of thermodynamics, but with a richer type of problem. Now let's look at what happens when I have open boundary conditions. For open boundary conditions, we have these points where we have the non-Bloch band collapse that are very interesting points, in addition to these points where we have the gap closing, right? So now I have this phase diagram, and let's look what happens at these 3 phase transitions here. So the first one from the Hermitian trivial to the Hermitian topological, which is that one here, I am representing it here for the 0 chemical potential in blue and in green. The blue one is for the extensive part, and for the green one is for the non-extensive part. Basically bulk and boundary. So I immediately see that for the first derivative of omega, for the green, for the non-extensive, I am seeing a jump at 0.5 and a spike at 1.5. So this is a first order phase transition for the edge. And for the blue, I have, here is difficult to see, but there is a little, a very little kink. And here also looks like a little kink. And actually I need to go to the second derivative to see the spike. It is a second order phase transition. So it's precisely what we knew from the Hermitian models. First order for the edge, second order for the bulk. Okay, but now when I look for mu equal -1, I am trying to look at this phase transition here. I will see that for mu equal -1, for the extensive and for the non-extensive contributions, I'm seeing spikes here when delta is equal to this value, which is precisely at the non-Bloch band collapse that is here. Okay, so now it doesn't look like it's the same derivative, the first derivative. It doesn't look like that bulk and edges are behaving different. They are behaving equally. It's a very strange thing, very strange feature. And what we can do, we can go into the periodic system using the surrogate Hamiltonian, for which we do the analytic continuation in momentum. And I can now look at this orange one, and I will see again the same spike for my surrogate Hamiltonian as I was seeing here for the orange. So things seem to be consistent. But we need to look now at the scaling to try to understand further what's going on here and here for these novel phase transitions. So let's now look at the transition from the Hermitian trivial to topological and at the phase transition from the non-Hermitian trivial to topological. One is represented in red, the other is represented in blue. Okay, so for the red one, I had precisely what I had before when I look at the scaling of my gap as a function of P, or at the scaling of my gap as a function of G. For several orders of magnitude, I get my critical exponents. Z is 1, mu is 1. I am in the Hermitian-Dirac universality class for this phase transition. The order of the phase transition is D plus 1. It's first order for the edge. It is second order for the bulk, as before. But if I am at the blue point, now my Z is 1/2, my mu is 1, my order of my phase transition is 1.5. I am in the Dirac, no Hermitian Dirac universality class, and the order of my phase transition is 1.5 for the bulk. And I can also, if I look as a function of G very closely, what I can see is that the singular part of my free energy is changing from 1 into 1/2 as I approach the phase transition, which is at 0. So only very close to the critical point, I will see that this critical exponent is 1/2. If I look further away, I have the impression it's 1, but as I approach the phase transition, I see that it becomes 1/2. Okay? So that is something different that we have for the non-Hermitian models. So the red one is in the Hermitian-Dirac model universality class. This is for the non-Hermitian Dirac model universality class with this complex coefficients alpha and beta that I have shown you in the previous slide. But this hyperscaling relation keeps holding for both. It's just that I get a different number here, but it still holds. But now let's look at this one here, at this non-Bloch band collapse. Now, for the scaling at this non-Bloch band collapse, everything becomes a mess. So there is no scaling with P. If we try to calculate the correlation length by looking at the correlations between C dagger I and C dagger and Ci plus R, I see something very strange. My correlation length is coming to 0 as a function of G at the point of the phase transition instead of diverging. So things are getting localized at the boundaries instead of extending everywhere when I have a critical system. So it is a very different behavior than I have in any critical system. It's very special. And there is a new length scale that is going to be associated to the imaginary part of K. And this is this so-called, due to the so-called no-Hermitian skin effect. So I have a skin length scale that's coming in. And now for this phase transition, the Josephson hyperscaling relation breaks down. It does not work. So you can see here that I had my mu z equal to 1/2 and 2 minus alpha being 1/2, and my omega s is 1/2. So the scaling in terms of G seems to be going with an exponent 1/2, but mu is ill-defined. I cannot define any longer my Josephson hyperscaling relation at this point. It's a completely novel point. And at this point, the extensive, the boundary and the bulk, they have the same scaling, as you can see in orange and in pink. So it's a completely new type of phase transition. So let me come to my concluding remarks because it is time. So I have been telling you that no-Hermitian systems can lead to very interesting and new phenomena. We can use a thermodynamic description if we have the appropriate symmetries, and we can still have a real partition function to attempt to describe these systems using thermodynamics. We have seen that the no-Hermitian systems have a different universality class with respect to their Hermitian counterpart, and that at the non-Bloch band collapse, all the scaling laws break down because we introduced a new length scale for these open boundary conditions. So with this, I conclude the talk. I would like to show you the pictures of the heroes who have been doing this work. So both papers for the non-Hermitian model and for the Hotchkiss were done by Rodrigo Arouca. He is the main author in both of them. The Hotchkiss were done in collaboration with Sander, and the non-Hermitian was done in collaboration with Qinghua Li. I would like to thank both of them, and now I would like to take your questions. I first listen to the questions, and afterwards I will show you my next slide for the question we already had.
Okay, there is one question. Mikel Garcia needs to ask about the fractional derivatives.
Yes, how are the fractional derivatives? So we have been studying, we have been learning at the university just first and second derivatives, right? But you can wonder, why does it need to be integer? Why can't I have a derivative 0.3 or 1.4? In principle, we could. So there has been, the mathematicians have been thinking about that already for long. Many of them, Riemann, Weil, a series of mathematicians. And it was extremely complicated because then you will get things that are completely counterintuitive. The derivative of a constant will become a function. The derivative of the exponential is no longer an exponential. So we started studying this problem recently, and there is a paper that was published last year, or this year, I don't know anymore, in PRB letters. We were looking at a fractional derivative of the Langevin equation, where the friction term is no longer a first derivative, but it could be any derivative, which is no integer. And it's extremely interesting because just by changing the number of the derivative, we show that we can, with the same model, describe many different phases of matter: liquid, glass, anomalous glass, the Gardner phase, and even describe a time glass phase by simply changing the derivatives. So if you go to this paper, which is on arXiv, if you look for my name, you will find the fractional derivative of the Langevin equation. In the supplementary information, we have a very long description of the history of fractional derivatives and how we could then tackle physical problems only when we got the Caputo version of it, because now it gives us boundary conditions in terms of integer derivatives. There are different ways how you can do. You can get several references to even books in our paper there. I invite you to go there. And if you would like to discuss further, please just drop me an email. I can talk to you further about fractional derivatives, because it's a topic we are currently investigating in the group, and we want to go on with it. It enlarges enormously our perspectives in physics. Thanks for the question. Are there more questions?
I have a question.
Yes.
So the non-emission systems you studied had a real spectrum, and
Yes.
I think there's, I think most of, if not all of the non-emission systems that have a real spectrum can be mapped to a Hermitian system by some transformation.
Okay, so let me, oh, this is a very good question, thank you. I didn't consider the ones that have a real spectrum. I consider the ones that have pairs of complex conjugate energies. Okay, the energies are complex, but they come in complex conjugated pairs. So when you sum over all of them, the imaginary part disappears for the free energy, but the energies is too complex.
Is it particle hole dagger or something?
Yeah, so this is the one I had shown you here.
Okay, sorry, so then I misunderstood.
Yeah, that is this. Yeah. You see, it's the pseudo-Hermitian.
Yeah.
And the SSH model, which is non-reciprocal, is precisely pseudo-Hermitian. So I still have complex energies, but the Z is real. That's the trick. For the other one, it is, if the energies are real, then it's simpler, of course.
Right.
You can see that here, I had a phase. I have these phases, which are the non-Hermitian trivial and the non-Hermitian topological. They are not connected to the Hermitian trivial to the Hermitian topological. Right. So I have genuine new non-Hermitian topological phases. And that's why I have here a genuine new universality class, which is the non-Hermitian Dirac universality class. Okay? So it is important to understand that I am still within a rather closed set of models for which I can think of a thermodynamic description, but I am capturing features that are beyond the Hermitian ones. And especially I'm capturing that non-Bloch band collapse, which is extremely interesting because it doesn't obey scaling laws, like the Josephson hyperscaling relation. Is it clear, the answer to your question?
Yeah, thank you. Sorry, I got distracted. There was some phone call. Yeah, it's clear.
Okay. Are there more questions?
So if not, I have to go. Yeah, there is more, but let me just go to the question that we had in the beginning, because I promised I would show how the Vanier how the Vanier spectrum is constructed. So you will construct the Wilson loop in that way by going from the overlaps of the UNKIs with plus delta K up to the K minus delta K. You will close your large Wilson loop. You will have to use this SU of M matrices where the M are the number of the occupied bands. Your delta Ks are defined here. And out of this, you can define then your Vanier spectrum. And once you have your Vanier spectrum, your Hamiltonian is such that you have the Vanier centers as the eigenstate, as the eigenvalues of your Hamiltonian. And once you have the Vanier spectrum, you can define the Vanier thermodynamic potential by summing over the Vanier eigenstates. maybe the best would be to go also to the paper and take a look. And if you still have any question, you could talk to Rodrigo or to me. Just drop us an email. Maybe this would help you to understand, the one who had this question before. And apparently there is one more.
There is one more question if you have time. Okay, sure. This is the last one. For the rest of the attendees, please write on Slack. So Isidora Araya Day says, I am not sure whether this was mentioned, but is it possible?
Sorry, I didn't hear.
I am not sure whether this was mentioned, but is it possible to somehow include disorder in this thermodynamic approach?
We didn't until now. I don't know. I don't know. It was not mentioned at all, and I didn't even think of it until now. Yeah, I don't know.
Can I make a compliment on that? Yeah, because in principle we can, because we can compute the eigenstates of the Hamiltonian in both real space or in momentum space. So if you add disorder, you can model it in the Hamiltonian, and in principle we can see the effect of this in the thermodynamics in the same way.
So, yes, but then not in K space, but going into real space,
exactly,
right?
Yes.
Yeah.
Yeah, only doing
but then everywhere where we were using these mappings that we just calculate things for the periodic boundary conditions and subtract, then you don't do it in K space any longer. It could be a bit more intricate. Yes, but thank you, Rodrigo. In principle, if you go into real space, I think you are right. One could try to do that.
Okay, so there is one comment as so you don't rely on the translational symmetry. And please, the next question on Slack.
The next question is what?
No. If they have more questions, they should write it on Slack because we are very late.
Okay, yes. So if you have more questions, please just send me an email.
Yeah, well, the last one was that you don't rely on translational symmetry. This is what she asked.
Well, when we have translational symmetry, when we are calculating, for instance, things in terms of K, for the bulk, we are relying, when we are calculating for periodic boundary conditions. When you have then the open boundary condition system, no, you are not. We can calculate things for open boundary conditions, but then to extract the parts we are interested, like the edge or the corner, we usually use this correlation function, subtracting the ones for the bulk, for which we are relying on translational symmetry, from the other ones. And that's why we had to define the surrogate Hamiltonian for the non-Hermitian one. So we don't need to rely on translational symmetry. We can calculate things using scaling, which will not rely on translational symmetry, but it might be much more costly in terms of time. When we can rely, we do, because this makes our life easier. But strictly speaking, we don't need to rely.
Okay. All right. Thank you very much for these two wonderful lectures, Cristiane, and I hope I will see you in San Sebastian.
Yes, I hope to see you in San Sebastian sometime. Thank you very much, everyone.
And for the rest, we will reconvene for the last lecture talk at 10 past with Sami Mitra, the editor of Physical Review Letters. See you soon.
Bye.
Bye. Hi, Shomi. You want to share your screen? Maybe you can start now.
Yeah, hi, let me start. Can you hear me?
Yes, and I can see
Okay.
you too. You are on the cover.
Can you see it?
Yes.
All right, I'm going to make it full screen. I can't hear you now.
I wasn't talking.
Oh, yeah. Oh, sorry. I was looking at the YouTube stream and I think there's a delay. Okay, good.
Okay, so this is the last lecture of the last day of the school, and we have a special speaker with Shami Mitra, an editor from Physical Review Letters, and he's going to explain us how to publish, get papers accepted in Physical Review Letters, and how to present our results, publications, and dissemination. And he said that he would like to have a lot of questions. So Shami, whenever you want.
Okay, thank you, Maya, and thank you, Adolfo, and to all the other organizers for inviting me to do this presentation. Now, of course, in a typical in-person presentation, I would basically have made this a complete Q&A session. And in that sense, of course, this is not a physics talk, and it's very far removed from any topological phases of anything. And so like Maya said, I'd be very happy to get interrupted with any questions. And we go through to the end of the session. And it doesn't really matter if I don't get through many or even most of the slides, because after all, there may be things that folks here are interested in hearing about, which I have not explicitly scheduled myself to speak on. I will try to swap between two presentations, if I may. I hope that'll work out well with Slack sharing. We'll see. So basically, what I wanted to and again, just stop me at any time, either through a chat to Maya, because I don't see the chat here at my end, because I'm in full screen mode, or just raise your hand, and I guess, Maya, you'll interrupt me and ask the question.
Yes, I will.
Okay, thanks. So I wanted to give you a sense of, when we talking about conveying physics results, what we have typically is, the pieces of the puzzle, if you will, are limited. We don't, what we have are posters, talks, and journal articles, essentially. And then, of course, what depends is, as the audience gets larger, as you try to disseminate your physics results, the expertise in that at the average audience member is far removed from what yours is. So typically, at the very beginning of one's career, or at an early stage, what you are typically presenting are contributed short talks, perhaps 10 minutes talks and so on, and posters. So there, of course, the number of people in your audience is small, but the expertise amongst those audience members is large. So these people are more or less working in your field, and that's why they're there. So you're kind of talking as if to colleagues in your own field. And then, of course, you have papers that come out of it, which are papers for specialized journals. So, for example, if it's something on flow cases, physics and condensed matter systems, you might publish them in a journal such as PRB, where again, your readership is mostly people in your field. And then you go on to invited longer talks where it could be a colloquium level presentation where audience members may be in completely different fields of physics or even different fields of science. And then you get papers for journals that are of broad interest, either in physics, such as PRL, Nature Physics, and so on, or at some level, even beyond physics, such as Nature Science, etc. And then, of course, eventually, I think one of the challenges of all scientists, particularly, including physicists, is that you want to, at the end of the day, convey your results to the broader public, most of whom are responsible for funding your research at a basic level. PRL in particular, I would say, has what I term as a balancing act. And I'll explain what I mean, that we are trying to cover 4 kind of constraints, if you will, which sometimes, even to me, seem to be mutually exclusive. So what I mean by that is we have a certain size. So PRL publishes about 2,000 to 2,500 papers in a given year, while that is substantially fewer than what we published about, I would say 5-6 years ago, when we used to publish about 4,000 a year. This size is still an order of magnitude larger than other broad interest physics journals, such as Nature Physics, or even our own Physical Review X. However, the size allows us to do 2 things. One is it provides breadth, in the sense that we publish in all areas of physics. So PRL publishes a substantial number of papers in fields ranging from high energy particle physics to plasma physics, to soft matter physics, to, of course, condensed matter physics. But at the same time, what this size allows us to do, that in any given field of physics, we are able to publish enough papers that if you're in that field, you get a sense that most of the important steps or developments in the field for a given year are being represented in the pages of the journal. So, for example, if we publish plasma physics, our intention is not to publish 1 or 2 plasma physics papers a year, but to publish a substantial critical mass of plasma physics papers, if you will, that provide a sense of what's happening in the world of plasma physics in that given year. But at the same time, we are exclusive in the sense that in any given field, we are publishing very few papers. So our acceptance rate and such are not particularly high. And so there's that. So it's kind of a balancing act. And we do have, and I think one of my next slides would tell me that this balance between exclusivity and breadth and representation provides challenges for us, particularly in very topical fields. So just to give you a sense. This is a slide I just as a kind of, PRL, of course, as most of you know, has done very well in frontier top flight physics over the years, so much so that in the last 10 consecutive years, PRLs have been cited for the Nobel Prize, Physics Nobel Prize. So this is a sense of what PRL publishes today. This goes up to 2016, but the numbers in 2016 are essentially similar to the numbers in 2006. So you see here, you cannot see my mouse, is that correct?
Oh, I think we can.
You cannot see.
We can.
You can? Okay.
Yeah.
Oh, wow. Okay, so you see that here, this condensed matter structure and condensed matter transport to me and to most condensed matter people is an artificial separation. So really, if you look at the numbers, the bars in red are lower on average than the bars in blue, because as I noted before, we are publishing fewer papers today, the same as 2016, than we used to do a decade earlier. On the other hand, you can see that the bulk of the journal really, in terms of absolute numbers, is condensed matter, structure and transport, and soft matter, which, I mean, there's more of an overlap. There are some areas in the journal which have a whole different field. So for example, particles and fields include papers, experimental papers, for example, from big collaborations like the LHC or Fermilab or SLAC and such. And those are sometimes papers with thousands of authors, but of course there's just the one paper. So that's substantially different. Now, just to give you a sense of how the challenges of subfields develop over time. So I just looked this up yesterday. So in the year 2020, that's calendar year of 2020, we received 154 papers, where just a search on the words, I mean, these are very topical areas. So on the Boolean and between non-Hermitian and topological in the title or abstract, 154 papers were submitted to the PhysRev journals, all of them. The number for that in 2010 was only 3. So you can see how quickly fields can develop. And you have so out of these 154, 70 was submitted to PRL, and then eventually PRL published 20 papers out of that subset, which had those 2 keywords in their title or abstract. That 20 was 0 for PRL in 2010. So that gives you a sense of what fields are. I mean, there are particular fields that suddenly get extremely topical. We can think of other fields such as magnesium diboride or nictide superconductors and such, where the topicality rapidly changes from even year to year. And then the other challenge for a journal such as PRL, and this of course applies to other journals, including several of the nature journals these broad interest journals, is some fields which we clearly consider to be physics at some point in time, then at some later point in time may not be physics anymore. So to give you an example, graphene in the early years of this century was clearly in the territory of physics. I mean, most of the papers appeared in physics. The Nobel Prize was given out in physics, and I think the people who were working at that time were mostly physicists on graphene. Now you fast forward a decade, and this was a statement by the conference organizers in 2017 at this meeting in Athens. And you can see the keywords that are, according to them, appealing to participants, right? And so the keywords are words such as optoelectronics, biotechnology, materials, renewable energy. And so it is unclear at this time whether the study of graphene is a physics enterprise, so to speak. And I think if you go to a typical meeting, such as Graphene or Graphene Week, in 2022, and you look around and you talk to people, I would be surprised if more than 20% of them come from a physics background. It is clearly different from what the case was a decade ago, but also importantly, it differs from field to field. So for example, if you go to a meeting in nuclear physics, for example, most of the attendees at such a meeting will be from the larger world of physics. And that situation would have been roughly the same 20 years ago. So there are some fields which are moving in and out of the world of physics and hence out of PRL's orbit, so to speak. And some fields are squarely in PRL's orbit over time. And so this is also reflected in where papers appear, where papers are submitted, where people perhaps should submit their papers and so on. But this is a constant challenge that we have to tackle in our journal. I'm going to stop here in case I'm just going to give you a few stats about the journal. Does anyone have any questions about anything or any, shall I veer off into something else or keep going? Anton has a question.
Yeah. Okay, I'll let Anton go and then I can ask my question.
All right. Yeah. If that's okay, I'm going to use my panelist and I'm just going to say the question. So this is actually quite interesting. You mentioned several constraints that that PRL applies, and I wonder about two things. First of all, you aim for broad readership. But actually, how do you know that you reach the aim? So how do you have evidence that people from different communities are reading papers that are not about their own work? That is one aspect of the question. Another aspect is I think that at least historically, or at least some of the PRL's constraints are there for historical reasons, like 4 pages don't even exist these days since there are no pages anymore. So do you think that...
Yeah, I'll answer your second question first and go to the other one, because the first one is an easy answer is we don't really know. But the second question, I think you're right in that as you said, the 4-page constraint is self-imposed and historical. That's true. On the other hand, in the world of physics, in particular, we think things are different compared to some years ago, but it's not so much different. So for example, pretty much in all journals, we still have a concept of an article. So if you go to any journal at the base level, of course, we still have an electronic entity, which is pretty much all the time a PDF article. I mean, they do have a web HTML rendering of it, but I don't think there is any journal in physics which does not have a PRL, a PDF baseline, if you will. And what that means is at some point in all journals, not just PRL, you have like a timestamp, if you will. Like, okay, here is what the published entity is, and this is different from what was on the archive 3 weeks ago. And if the archive entity changes, somebody puts a date on it. So that limitation is unique, I think, more so in physics than something else. Just to go to the very general non-science world, right? If you just this morning, let's say I'm looking at the New York Times, I'll give you an example, and we happen to live in New York, so we get the paper copy. And the paper copy is a piece that is frozen in time as to what it was at 2 a.m. or 1 a.m. in New York City area. Now, of course, if you go to the website, right off the get-go at 6 a.m., it's very different from what the paper copy was. Not only that, if you go at 6 and at 6:30, there are different entities. Things are moving. And there is really no concept, I think, anymore of what is an archival thing. So if what is the New York Times front page on the 27th of August, which is an easy question to have answered 20 years ago, you cannot answer it now. But in our journal, so at the base level, I think if it turns out that the world of physics decides that this PDF, which is really just an electronic rendition of what is thought of as a hard copy, does not matter, everything should be a fluid, fungible electronic page, if you will, then I think we would have to change. I think our current position is that this 4-page limitation, which does affect us negatively at times, because there are times when we would prefer to have long, the authors who submit to us would 8 pages would be much better than 4, let's say. If the argument is 30 pages would be better, then our decision is somewhat clearer. We'll say, just submit to a journal without the limitations. But sometimes, indeed, 8 would be better than 4. I mean, it's not 4 anymore. It's become a little expanded because we count. But anyway, that's what it is. And then, of course, we have moved into the world of supplemental material, which has pros and cons. I can go into it if you want, but so that's added on to the end of it. And we also have 2 other things, and then I'll move on. For certain papers where the editors have determined that it is worth the journal's while and also for readers to have a longer paper, we do allow additional length. So every once in a while, you'll see PRLs which have 6, 7, even more pages. I mean, we famously, the Bicep 2 paper had 20 pages, but that's a whole different. I think the LHC paper, the gravitational waves paper had more. And then also we strongly encourage, and we facilitated that fairly well, I think, joint submissions to PRL and let's say FISREP B at the same time, and they supposedly can move along fairly smoothly through the process. And that way, I mean, the downside of a supplemental material is that it's not a citable entity and it's just sitting there, and you know of its existence only if you land on the journal article, but otherwise you wouldn't. Whereas if you have a separate journal. Anyway, so that's some of the issues, but I'll continue. And did somebody else have a question, or I don't remember? Adolfo?
Yeah, I think I have a question on the burden per editor. Is that similar to other journals, different, or are you like overwhelmed?
You mean the number of papers handled by an editor in a given year?
Yeah. Like, is that comparable to other journals like Nature Physics, or
I think it's well, I mean, there are two. One is the absolute number of papers that come in. I think they're roughly comparable. It's not an order of magnitude difference, but I think the difference a little bit between PRL and perhaps some other journals is, and we can, I mean, discuss this if you wish, but I think PRL currently, I suspect, rejects 30 to 40% of incoming papers without review. And a typical editor in the journal is handling, let's say, 600 to 800 papers a year. So a third of those papers are, let's say, are rejected without review, which means that 2/3 of them are sent out to referees, and not all of them entail the same amount of work and so on. So roughly, I think that if you just look at the absolute number, I don't think there's a order of magnitude type difference, but how much work goes into a paper or how many papers are reviewed and things like that may differ from journal to journal. I see a question and answer. Shall I click on it, or is somebody going to ask me? Let me see.
You can click on it and read it, or I can read it as
okay,
well.
I'll read it. So the question is, how does this going in and out of the, in quotes, physics zone happen? Is it, for example, purely the number of papers that get submitted from an area to PRL? Do you monitor this change of trend actively? I think if you mean by monitor it actively, whether we are doing it live at the time, not really. On the other hand, do we have a sense of these changes with the benefit of hindsight? Yes. I mean, this is not just in terms of the journal, but you can, anyone can go to, for example, a Web of Science or NASA ADS or the archive and get a very clear sense as to spikes in particular fields in physics. I mean, the archive is a good place to see because, I mean, the only people submitting, let's say, a graphene or 2D materials paper to the condensed matter CONMAT archive are mostly physicists. And so you get a sense of, what do they come from, a physics background or a materials or chemistry background, and that these kind of changes, I think, are happen in many other fields, but in physics in particular. And now, of course, the definition, I mean, there are fields like materials science or energy research, and the question of what's physics and what's chemistry is in some of these areas somewhat fluid, I think. And as I noted before, in some other areas, such as high energy physics or particle physics or such, is it physics or is it something else, is, I think, more clear cut. Oops, there's another question. No, that's it. Okay, so I'll continue and just chat or. One of the things I think people may not recognize is that the journals of physical review, and not just PRL, are very global. 2/3 of our, even this 2/3 is old news, I would say 70 to 75% of our papers come from outside the US, and referees are from outside the US, and even the revenue from the journals and all. So it's a very global entity. Here are some numbers, and you will see from here that basically half of the published journal is from Europe now. And these numbers are from 2017. I am a little embarrassed that I should have updated it for 2021, but I think numbers will not be that different. So this gives you a sense of where, and again, some geographical areas are showing sharper growth in absolute numbers, but more in proportional numbers, fraction of published papers than other areas. The referees, of course, are also equally come from a very international background, and this has changed over time. I think 15 years ago, it was much more US-centric, if you will, the referees, more so than the papers. But then several recent developments, and these are good things that the internet gives us, as opposed to many other things which are not so good. One of them is that entities and pages such as Google Scholar and all have made it much easier than before to get a good global sense of who is publishing what in what fields, who are the active people, and so on. And so this kind of literature search and searching for referees and so on has become much more democratized, if you will. That's the first thing. And the other thing that has happened, and that happened a few years even before that, is that everything is electronic, of course, now. And so there is this concept, there's no physical mail-related and such delays and considerations between whether a referral, for example, is being sent from New York to Australia or from New York to Chicago. There's no difference. I mean, these kind of things used to matter once upon a time, which were self-limiting constraints. So this was a question. As I said, I have a separate. I was going to say it's a Q&A kind of thing, and people ask all kinds of questions, which I have some slides on. But this was a very broad, bird's eye question. So these are the biggest challenges on the horizon for scientific publishing. So these are. So I have a slide for what I think these challenges are going to be. Well, as you can imagine, there are some challenges, and most of which we do not know the answers to. The first is the concept of peer review here to stay? I don't know. I mean, it's possible that there are other areas where reviews of entities have been democratized, such as product reviews and so on. But at the same time, they have journals where one or two individuals review things and they abstain. So we don't know. All indications are that at this point, it is here to stay. And one of the examples I'll give is, for example, there are areas on the archive, in particular, let's say HEPTH, it's a high energy physics theory papers, where every paper that is submitted to our journal, for example, has been on the archive for sometimes weeks before they come in. So, and most practitioners in those fields access that material through the archive and not through the journals. So the question remains as to why are journals in high energy physics doing quite well, perhaps even better than they ever have. And that's because for whatever reason, researchers still find it useful to submit to journals. I mean, one can argue as to those reasons should exist or not, but that's a different point. I think the reality is that at this time, the journals are not the sources of dissemination so much. No one needs the journals as such to access the information, but they are still there to provide a stamp of validity and the value of peer review. Second question is this reliance on metrics such as impact factor, H index, and so on, and how this should play out and whether this is good or bad are decisions from hiring to career movement, and so relying too much on these journals are becoming. So these are questions which will change over time. I think we don't know the answer. The answer, I think, today is that perhaps yes, we are over relying on metrics, but how it will be 5 years from now, 10 years from now, we don't know. Social media. In some fields, social media has taken over considerably, and everything from sales of books to what kind of epidemiology the average person knows is driven largely by social media. In the world of physics, it's less, I think, prominent than it has been in some other areas. But then, there are, I could talk more about it in person, but there are. So social media plays a role, but not to the extent that it does in some other fields of research or even in other fields of science. And then free viable. That's a big challenge, right? So Google Scholar and the archive provides access to every, theoretically could provide access to every article that's published in the journals. So at some point, if you have the access to the articles combined with some kind of vetting process that is independent of the journals, then of course, things are different. There's the whole challenge of open access versus subscription model that's ongoing. And the last one we already discussed in response to Anton's question, that what is a paper after all? If it became some kind of fluid entity, then the roles of the journals may change. We don't know. I'm going to skip this. So one of the questions is, why are there journals still around? I think one of the things we can talk is that journals do certain things that just a web posting on the archive or similar does not provide. So of course, dissemination, but one could argue that dissemination happens with the archive. But if you want to go, and somebody had this question before, slightly cross field, if you have a paper which is talking about some aspects of layered materials that may be of interest to somebody who is doing, polymer physics, for example, if it's sitting in ConMat alone, they may not see it. So there's that. There's, of course, the stamp of validity, which is important, that this has been peer reviewed and has appeared in this or that journal. And some people value those particular kinds of stamps, if you will. Curation is always important. So, there are 1,000 articles that might appear on a particular time frame on the archive, but the non-specialist might say that I don't have time to look at 1,000, tell me which 50 I should look at. So the journals perform that role. It is not a given that the journals alone should perform that role. It's entirely possible that you could have other individuals, for example, that people may trust. Highlighting is very important. So for example, when you have a particular development in physics that then is covered by the news media and appears in the pages of a prominent newspaper, it's almost never the case that the journalist is looking it up on the archive and then deciding to highlight it. They are looking at the journals, and the journals certainly the more prominent journals have a fairly well-established kind of way to reach out to journalists. There are journalists subscribed to their soon-to-be published lists, and they have correspondents of the people hired for that purpose. So there's that. We already covered about the journals and their impact on non-journal decisions, such as getting tenure, promotions, hiring, and so on. This may be fortunate or unfortunate, but that's reality. And then, of course, outreach to a wide audience, that's very important. At the end of the day, as we all know, the ongoing challenge for scientists at large and physicists in particular is that we do want the non-technical, non-scientist population to have some sense of the importance of what we do. Because at the end of the day, if the general public gets disinterested and unaware of what presumably good work that scientists are doing, then that's not good for scientists in particular and population at large. All right, I'm going to stop again in case somebody has any questions. I'm going to just say a few words about our review process. Any questions, anyone? Through the chat or through Adolfo and Maya? All right. All right, so PRL's review process is probably fairly similar to that of other journals. The most important thing to tell folks here is that most papers that come into PRL are usually very good papers. So most papers that are submitted to PRL are not ones that are clearly incorrect or clearly invalid. And so once, we have this, as I mentioned before, the subset of papers we do not send out to referees because our sense is that even if this paper is deemed to be correct, there's nothing wrong with them as far as the science is concerned, it would be very unlikely that we would publish it. And so those papers we do not send to referees. However, of the papers that we are sending to referees, a large fraction of them, a majority of them for sure, are not ones that the referees eventually tell us that their science is incorrect. And then, of course, once we have determined that the science is correct, then the decision to publish it or not publish it at some level becomes subjective. And so that's the first thing to remember, that from the author's perspective, they submitted significant, important, correct work to PRL, but the journal, in many instances, is not publishing that work. And the question is why? And that's largely because the journal has some a sense of the threshold and their estimation with the knowledge of the paper, what they know of the field, what the referees have told them, the editor's knowledge, for example, has not persuaded them that this paper is above that threshold. So that's the. And the other question is also we ask ourselves, and this is again something which is not a precise objective thing, is that we are looking for a reason to publish a paper in PRL, is why this paper should be published in PRL, because it could have been published in some other journal, and we're looking for a reason that tells us that it should be in PRL and so that reason again is it's at the end of the day slightly subjective. And now here's some for the folks who are in this session who are perhaps early-ish in their career. So kind of making a case for publishing your paper in PRL. So here the scenario is that you're trying to persuade the editors and the referees as to why your paper should be in PRL. Presumably you have convinced yourself that it should be in PRL because that is why you have submitted to the journal. So the first step, and this is of course one of the, I always try to show this, is that because when a paper is submitted to any journal, it's certainly a journal that is read by people who are not necessarily experts in your field, keep things simple. Omit needless words. Do not use terminology that would be only meaningful to extreme experts in the field. Because remember, at the end of the day, PRL is a physics journal, but not a journal in the subfield of physics that you're working in. The best way, I think, to do that is to, once you've got the paper in a form that you think you should be sending to the journal, ask a colleague who is a physicist, but not someone in your field, to read the paper and give you feedback. If this colleague is unable to understand at least the introduction and the conclusion, then tell yourself that you have a problem, in that referees and editors will have similar difficulty in understanding the paper. All parts of an article are equal, but some are more equal than others. And so the interesting thing is that there are some parts of any physics article that stick out first and foremost in the minds of readers than others. So we got the abstract. Sometimes it's just the title. And just to so the title in the year 2021 has a greater significance than, let's say, even a decade ago. And that's because of social media, for example. Twitter, when people are tweeting about your paper, and it hopefully pre-publication, but certainly post-publication, getting some traction in terms of publicity, often only the title is floating out. when you post your article on the archive, people look at the title when they land on the page. To look at the PDF, they have to take an additional step and click on a link. They may not click on the link if the title, or if they're familiar with the names of the authors, perhaps they'll click on the link, but otherwise all they're really relying on is just the title. So the title is important. Make an effort to make this title as broadly understandable as you can while still remaining true to the content of the paper. Abstract, similarly, the abstract now has a newer role compared to 10, 15 years ago because of keyword searches. So the abstract often is almost like a collection of important keywords written in a form that makes a nice, coherent one-paragraph précis, for example. Introduction of the paper, the figures, the conclusion, and the references all are important. I mean, often people will try to get a gist of the paper after what we call a quick read. And a quick read essentially means looking at the introduction and the figures, and then looking at the figure captions, for example, and then the conclusion. First impressions matter. You want people to want to read the rest of your paper. These are some of the things that you can provide to the editors in addition to the paper itself. So again, as I noted before, you're submitting to PRL for a reason. If you think you should help the editor understand that reason in the cover letter, please do so. If you think that we should or should not consult particular groups of referees, please tell us, and so on. And this is, of course, applies to many other sorts of responses, but when you are responding to referee reports, please help the referees and editors understand again and why the paper itself is important. So we often have scenarios where the submission or the resubmission letter is much more helpful and sometimes longer than the paper. And then that is indeed helpful, but the question immediately arises as to, well, the reader is not going to be able to see that resubmission letter. The paper has to stand on its own, and the paper is not making its own case as strongly as the resubmission letter is. So anyway, so that's kind of my presentation. I'm not going to I have a list of questions and such, which I shall, for now, I can go into them if people have other questions, but I'm going to unshare my screen so we can see each other. And if people have other questions, please ask.
Are there more questions?
Yeah, I can ask questions if if we need some time for people to write.
Okay, please.
So what is the what is the policy? Is there a policy for, let's say, unreasonable referees? Let's say you clearly see that there's some referees that clearly understood the paper. They made an effort to do a, let's say, a good reply, no matter if it's accept or reject. But then there's some like clearly substandard referee report. Is there, how does the editor act in that case? Like what are the steps? Is there a policy? Like, I mean, this case I described is pretty clear, but let's say,
yeah,
is there any policy?
Yeah, I mean, there are by policy. I think what corrective steps should we take, right? So
exactly, yeah.
There are two levels. Like, one is what happens with this particular referee for this particular paper. That's the one thing. So there, of course, what we have is this is one of the reasons we typically do not go to just one referee. More often than not, we're going to two, or sometimes if it's more than 2 rounds or more than 1 round, we're going to 3 referees. If the report appears to be quite unreasonable, either right off the bat to the referee, to the editor, that's clear. But sometimes the authors will make a good case as to why that report should be, has problems in addition to being scientifically incorrect or something. So we will often calibrate it by, and we do this more and more, we will go back to the referee and ask them for certain clarifications. Or we will try to, we call, harmonize, if you will, that's a term, by asking the other referees to comment on this report. And then of course, there are cases where the reports are really just not good at all, right? And then we will mark it as that. And then over time, of course, that's a separate issue, doesn't help this particular paper. We have, for every report, we have fairly detailed kind of assessment ratings that we provide in the database. And then over time, these numbers are collecting for a particular referee. And if, it's like a rating system and anything else. So if a particular referee over time is either takes much too long or the reports are just not good and so on, then these will be, there'll be a metric attached to the referee, which kind of collects over time as the, and so this referee then falls lower on the list of referees that will consult. But for a particular paper, so let's say you're an author and you've received a couple of reports and you find that one of the reports, certainly some reports will advise rejection, which you as an author will not like. That's a different issue. But there's a question of they've advised rejection, but in a manner or with particulars that you think clearly any reasonable expert in the field would find objectionable. And then you should point it out as even a point-by-point rebuttal, but certainly as a general matter to the editors. If only to tell the editors, hey, look here again, this referee report is just no good for this reason. And then we will, there's a PRL, I think, does have a process. At the end of the day, what, as I noted before, there's an element of subjectivity necessarily in that we are often making decisions to not publish papers which are perfectly correct and perhaps even fairly significant. And that's a different issue. That I think it's not whether a report is good or bad, but a decision may appear to be illogical to the author. But you have to have a global sense of it. So I'll give you an example. This whole thing about non-Hermitian physics I just mentioned, right? We are receiving so many good papers, if you will, on that topic, but we will publish, a certain fraction of them. Acceptance rate for this year for such papers will probably be higher than the journal's average, quite a bit higher. But still, for many of those papers, it just won't be, they won't appear in the journal. So.
Yeah, thanks. Maybe I can read a question here now that I'm here. So Mikel Garcia asks, how are authors that go into other fields maybe temporarily considered? Is there known expertise in their original field taken into account?
So it's unclear to me if they're asking whether the known expertise is
I guess if you have a
taken into account when they're consulted as referees or in looking at their paper when it comes in.
Yeah,
the looking
says authors, so perhaps he means
right. So let's assume. So is there known expertise in the original field taken into account when the paper comes in? Well, the paper is treated at face value. Sure, we are aware who the author is, and we have usually some sense of their track record in a particular field, but we routinely have authors who move from a field to another field and submit papers and so on. So in that sense, it's not taken into account in the sense that, oh no, this person has only published in quantum Hall effect, and now this new material called graphene has arrived. What do they know about this? No. They know gallium arsenide, but they didn't know graphene or something. I don't know. But no, I think that taken into account in that sense is just that, paper has arrived, we treat the paper at face value. On the other hand, it's not double mask review. We know the identity of the authors and so on. Now, consulting them as a referee, we will typically, in our own database, we have information as to what they have refereed before, right? So they may have refereed a bunch of papers in a particular field, and now there's a paper in a particular field, but they have just recently moved into that field. Our database, there's a lag. Our database is not going to reflect that, their new interest. However, we often will look at Google Scholar or something like that. And so in those instances, our knowledge of this individual's expertise is going to rely on either something which is organically growing quickly over time, like Google Scholar or the archive, where we have information about what they're just doing now. Or, we may have just been to a conference or something, and this person gave an invited talk, and then we're aware, oh, this is what they're moving into. But they have done good work in some other field. So yes, so the answer is yes.
Okay. There's a short question on whether it will be possible to have the slides. Yeah, if you feel you prefer to read it.
It seems as if there is an incentive, if you are rejecting a paper, to offer a very sparse report. That is, this paper is scientifically correct, but I do not feel that it rises to the level of impact necessary. Ever ask or ask the editors encouraged to ask referees more detail than we specifically rebutted. So the example here as like a one-liner, no good, that is not helpful to the authors for sure, but it's not particularly helpful to the editors. Now, on the other hand, I think the reality is, as I noted before, that our primary aim in PRL through the review process is the primary aim is always to get the referees to tell us if there's something wrong with it, scientifically incorrect, as far as they can tell. But as I noted before, more often than not, that's not the case. It's not that there is scientifically wrong with the paper. Then we are hoping the referees will tell us something about the pros and cons as to whether we should publish it or not, plus suggestions for the authors. And we are really looking for a reason to publish the paper. So if the reverse were the case, which is that the referee says, this paper is wonderful and you should certainly publish it. That to us is a bigger problem, because we will be very reluctant to publish a paper based on extremely unhelpful short piece of advice. If it's negative, then we will try to get more and we'll try to calibrate with what the other referees are saying, and we will recognize that this is unhelpful. And we might go back to the referee and all, but unfortunately, from the author's perspective, the ground state, which was not yet a PRL, remains, right? I mean, this paper is not being shifted above the ground state with any report. So there's that. So it's unfortunate these reports do come in on occasion. We don't, I mean, as far as the question also says, if there's an incentive to reject a paper, I mean, there's not an incentive per se, because PRL, as you know, the review process is, I mean, we have 1 or 2 rounds of review, and after that, being a society journal, you may appeal a negative decision. The appeal then, in some cases, will go to the divisional associate editor. Then we have a whole process. And so at some level, it is not in the interest of the journal editor to make arbitrary negative decisions, which to reasonable people will seem illogical, because then we are just making life complicated for later on. So we'll try to, I don't know if that answers the question, but yes, I can provide the slide of this later to Adolfo, and then he can send it over.
Yeah.
Okay, there was a question, some other question. Do you think it's possible that some metrics, as clicks on Google Scholar, mentions in social networks, would play a role when determining whether journals should push to publish in some field which is on the rise, for example? I not only think that it's possible, I would not be surprised if this is already happening. Of course, there are some fields. Google Scholar is, in terms of metrics, if you mean appearance of papers, there's 2 kinds of metrics, right? How many papers are being submitted in a given field, and then there's the citation metrics. Citation metrics now, of course, with something like Google Scholar or NASA ADS exists even before a paper is published, which is tempting, I'm sure, journals, and not just journals. I mean, I would say journals or department chairs or funding agencies are often making decisions as to whether a particular field is more topical than some other fields. I mean, I'm sure if you ask for funding from the from NSF or something, then they will pick and choose fields, right? I mean, they will say that this field is more topical than this other field and so on. So I don't think those decisions are based just on metrics on some entity like Google Scholar. But on the other hand, they could be based on factors that are not, objectively scientific, so to speak. And that's reality. I don't think that's any different from what the case was 50 years ago, except, we have social media now and we had word of mouth then or something. And one could argue that at least with Google Scholar and even social networks, it's more transparent. People see what's on Google Scholar, people can see what's on social network. If it was just word of mouth, a bunch of people sitting in a room and, some, Bell Labs or something, you didn't know what was, so.
I don't know if Anton has a question. Yeah, okay. He just raised his hand.
Yep. Some time ago, and my numbers are also a little bit out of date. I tried this a couple of years back. I checked how many papers on archive content have an APS-DOI, and I found that it's like 70%, which largely makes APS a monopoly on, or the biggest player in condensed matter publishing.
Yeah.
What do you think follows? So first of all, an impressive result, but also what do you think follows out of this?
I think, so when you said you checked, now, did you check mostly theory papers or all papers?
Just all the archive preprints, which do have
I don't
a DOI.
have any special insight, but off the top of my head, I can think of a few reasons, right? So one is, of course, the archive, even after all this time, and when we are thinking of ConMat or even HepTH or something, is largely the world of physics. I mean, so if you have somebody in a chemistry department working on TMDs, for example, and they are just as likely to submit to ACS Nano, I'm not sure if the archive, through their productive PhD postdoc years, has been an entity where they have posted routinely. So I think it's possible that when you are looking at the archive as a marker, then you are by preconditioning yourself to move around in the world of people who come from a physics background. There's that. There's the other thing, which also could be true, that physics, because of its perhaps real focus on what one would term basic science, is there's much more theory in PRL in certain fields than others. So if you take a field like topological insulators, for example, or quantum spin Hall effect, all these kind of topical subfields, if you look at the very substantial theoretical advances were published in PRL, but sometimes experimental papers not so clearly. And of course, then the corollary of that is that theorists are much more likely, especially in condensed matter, you can check for yourself, much more likely to post on the archive than experimentalists sometimes. And so that's another bias that plays into it. And then, of course, if you move into the kind of physics that veers towards quantum field theory, ADS-CFT, or even the topological phases of matter that people here, or you guys are talking about, I think you're kind of moving into the world of particle physics and all a little bit, and so there's that also. So I think all these reasons play a role. A test of this, a reverse test of this would be if you went to some big conference in, I don't know, again, 2D materials, let's say, where large experimentalist groups and all are, as I said, many of them don't come from a world of physics, and I would not be surprised if many of those papers are not on the archive.
Okay. Any other
Maybe we're all
questions?
questioned out here. Our 42, 33 panelists are still there, but I don't see anything. So I'm not panelists, participants.
I can ask a question on referees. Maybe Reyes wants to ask a question. Okay. Maybe not.
No, I was just testing my camera.
Okay. So when choosing referees, there's an issue of career stage, and you can choose postdocs or very well established scientists, or even like experienced PhDs, let's say. And so my question is whether that factors in the way you give to each referee report, and also considering the amount of time that at different stages of the career one might devote to actually referring a paper, basically.
Yeah, I think clearly, I don't think, there are people who actually do this kind of research. I haven't, but so it'd be good to see if there's a correlation between, is there a sweet spot in the career path, right? So you're obviously, when you're a grad student, you're not doing any referrals. So you're starting presumably in the later grad student or early postdoc years, you become a referee and so on. And at some point in your career, you probably hit a peak of how much you're engaging as a referee. And then once you reach a certain stage, many people will drop off. Not everybody. I mean, there are some people very established for many, many years who are very active referees. It's difficult to say. The correlation, of course, in our case in PRL is we typically add referees to our database who have either been refereeing for some other journals in APS journals and they have a good track record, or sometimes we'll search for them, do a Google Scholar search, and we'll see that a particular individual has been very active in the recent past. So last 3 years, they've been very active and getting papers published and so on. So we'll consult them as a referee. And sometimes we'll find that this person happens to be a second year, first year postdoc, and that's okay. And of course, as we all know, that there are some senior graduate students who may be much more productive and connected to any particular community than somebody who's, been in the field for 7 years. So there's that. But unless we happen to know the person, because sometimes what we'll have is, and we encourage that, we send a referral to a professor and they will say that I don't think I can do it, but my postdoc will be, is eager to help. And then if we see that the postdoc, is somebody who should have been in our database, but is not, but has a good track record, then we'll say, okay, great. Or we might say, would you submit a joint report with this person? And then the new person then gets in our database and is there from that point on.
Yeah, I guess. Oh, sorry.
No,
I guess just an interjection on the question. Like, I guess it matters also because you're taking into account a subjective matter, and then you might not have a late PhD or early postdoc might not have the same
that's true.
opinion
and
of
this
what
is why.
PRL.
Right. So the subjective matter, I agree with you that sometimes a different weight should be applied. And I think it's the job of the editor to apply that weight, to weight it differently. In other words, to the assessment, the way I see is that the assessment of the subjective element that I mentioned can be done two ways. One way is for the editor alone to make that choice. Of course, then all kinds of biases, including the editor's own bias, their knowledge or lack of knowledge of the field, and how connected or disconnected they are to the community. All of that plays a role just as much, except now it's just one point of comparison. Now, our attitude is that instead of a single point of reference, we kind of try to correlate 2 or 3 other people in the mix. And then, of course, we should be aware that, this referee provided a great technical report, but their assessment of developments in the field compared to other fields may not be as But this is also not necessarily tied to seniority. There are people who've been working in the field for 10, 15 years who may have a fairly narrow view compared to somebody who's kind of moved into the field, but is more willing to educate themselves.
I don't know if there are any more questions. It's already quite after time.
Yeah, I think we're.
Anton, you're smiling. I don't know if you have a question. We can give you a last question if you want.
Yeah, right. So first of all, I would like to return to our discussion in chat about the publishing of code and data.
Yeah.
And so I understand your statement that different questions have different communities have different standards. That's perfectly fine. But at the same time, on the one hand, and in some cases, there are really good arguments for not imposing a central policy. I also take that. But at the same time, on the one hand, problems of reproducibility are as valid in physics as in any other field and field of science. And you mentioned the engagement with the broader public. So for that, certainly reliability of the published results seems important. Also, so overall, I also didn't encounter strong arguments against requiring code or data. So I'm a little bit surprised to encounter the hesitancy to impose a policy there.
Well, I think I mean, again, I think that the distinction is the difference is here between requiring something and then having to police it, and then having to deal with communities who are resistant, versus encouraging it. I mean, there are three levels, right? Allowing, we're clearly there. Encouraging, we are there. We encourage, but we don't proactively encourage, in the sense that editors aren't going out and saying you need to do it, but if it turns out that it's there, or if referees tell us that it should be there, then we'll push the authors to provide that information. And the next level is requiring. Actually, I have just learned that requiring is a very high bar. Most journals do not actually require, in the sense that it is not as if they will refuse to publish a paper if that information is not provided. They will have a statement. They'll have a declaration statement of some sort. So we don't actually require the declaration statement, but I think and it's similar, as I noted earlier, to contribution statements. I think there are journals that require contribution statements or strongly encourage that this person did this and this person did the simulations, this person ran the code and so on. We don't, and partly it's because we haven't, and maybe it's historical inertia, but partly it's because in some fields it would be certainly extremely unpopular and therefore essentially unenforceable. I mean, we could change it. We could take a position that says we will not publish a paper unless you do this, but I think that's not a position we're willing to take now, because I mean, this is, of course, true in all kinds of areas. And as I said, the author, there's a length requirement. I mean, there are many instances, not just with journals, where there's a reluctance to require something, because as soon as you say required, then the next question will be, what are you going to do with people who don't follow? Are you going to not publish their papers? And our answer is we don't know. So. I think, on the other hand, if a community overall started pushing for it big time, and there are areas such as the field of artificial neural networks, machine learning, and so on, there is a sense that this data should be available. And then, if there's a general sense that every paper that comes in that we are reviewing, we're sending it to referees, we're getting to publish, referees are routinely asking this kind, then it becomes a community thing where everybody's But at the same time, if there's some other community, it's not like, so then, yeah. So then it's not required, because in a journal, you can't say if it's happens to be in this field. I mean, there are others. So yeah, so anyway, that's where we're at.
Okay, very good. I think we should start closing, because if not, we'll do a closing statement without anyone to close.
That's right. Please. Yeah. So I will turn off my camera, and I am not sharing my screen. So very nice to.
Yeah, thank you. Thank you for your very nice talk.
Great. Yeah, thank you,
for
guys.
being here. And please, please do send me your slides or put.
I will send you my slides, and if anyone has any follow-up questions, please send them to Adolfo, who will forward them to me.
Absolutely, yeah. And yeah, I'm gonna thank thank Jeremy for the nice talk, and all the rest of the speakers. And I think on behalf of all the organizers, I'm going to close this last session and last day of the Topological Matter School. I hope you register for the next one next year, which we hope we will be able to host you here in San Sebastian. If not, we'll be online, but still, nonetheless, something topological and something interesting. So thank you for attending, and I hope you got something out of it. Please follow us on Twitter and YouTube and so on, which those kind of things help us go on and justify the existence of the school. And thanks to all the speakers, and see you next year. Goodbye.